Okay, I think we're all ready now. Welcome everyone, and welcome to those who are joining us online. We're live streaming today, which is very exciting. This is again, my name is Molly Stolboff, and we also have Angela Thorpe up here. We are the graduate program managers. So you have probably emailed us occasionally before today. You maybe emailed us in our prospective inbox as well. So that's us communicating with you, and we'll also help take care of you when you come to school here. So welcome everyone to our welcome weekend. This is our first time back on campus since COVID. So we're really excited to see you on campus and coming here to Madison with us. Before we get started, I just want to, again, welcome everyone to the space and just let you know where to find some things. You may have noticed we've closed the door now, the wall over there. So if you do want to get some more coffee or some breakfast pastries, you'll just have to exit through the main doors to grab that. Those will remain available throughout the morning. If you need the restrooms, if you go straight out the entrance doors and just keep going, you'll see those just kind of to your left near the elevators. And there are single stall restrooms there as well. So I'm just going to keep it brief. And without further ado, I'll introduce our department chair, Professor Remzi Arpachi-Dussault, to get us started. Thank you. And the clicker is already not working.
Clicker's not working. Okay.
Is it on?
Is the clicker on?
Yes, it's on.
Something's happening. Oh, there we go. You did it.
Point
That's
it back.
good.
Okay.
Which way do we point? There. Okay, thank you. Hi, I'm Remzi. As you've just been told, you have now been locked in. So, so you'll be here for the next, how many hours? 4 hours. Okay, I can see your enthusiasm about that. In any case, I'm, yes, the department chair, outgoing department chair, which is why you can see I have a big smile on my face. I have 4 months left in my term. And other than that, I'm just a professor here. I've been a professor here for 23 years. I'm just going to tell you a little bit about our department. Let's see if this works. So far, no. Which way do I point it? Point and click right, the right button. There we go. So I'm just going to really talk about one thing, which is why come to UW-Madison, which is perhaps a question you're trying to answer. Okay, let's see if this works. First reason, place. This is like has a nice delay, so I don't know if the button clicking worked, and I have to sit here and do this constantly. So let's see if is there a better place to point? You've been doing it. Oh, you've been advancing it. So when I do this, you click a button over there. Can we have a better signal? Next. It's going to be a long morning if we don't have a clicker up here. As you can see in the computer science department, we have all the technical details smoothly handled. In any case, Madison, what is one reason? This is a beautiful picture of Madison, which you will see when you fly over in a helicopter. You can actually see our building in it, but on the next slide, you can see, yes, well, you'll just guess, I guess, that what's awesome about Madison, it's often you'll see this, it's voted the best place to live, almost in, there's every little survey that you see. And it's because Madison's like a big little city. So it's like a college town, but it's also the state capital. So there's a lot of stuff going on here beyond just college towns, but it has that college town feel. So it's kind of perfect. It's also the #1 place to move, according to David Pogue, in case of extreme climate change. So if you're planning ahead, I think Madison's a great choice. Okay, next. History, great history. We're going to flip right away to the next slide. Works for you back there. Maybe I should just stand in the back, but that would be a bit awkward. Department has a great history, actually. This university has played a pivotal role in the history of computing. That actually goes back to before our computer science department was even formed, where like John Bardeen was an undergrad here. He was won the Nobel Prize for his creation of the transistor. Gene Amdahl, who was one of the first makers of computer, real computer architecture pioneer, got his PhD here. And the history of our department, the second department in the country to be formed, just fantastic. Just people like Steve Kleene, who invented things that you may have heard of, like regular expressions. Barclay Rosser, famous theoretician. And then I found this letter from Alan Turing to his sister, and he talks about people, which is kind of fantastic if you think about it. And why does that matter? Well, it's kind of cool, but it's also because those are the people that hired the people that hired the people that are here, right? So it's kind of like the history of people here. Okay, next. That's history. Next slide. It's just not working today, huh? I think you're just gonna have to sit back there and advance them when I say next until you figure it out between talks or something like that. Okay, research. Next slide. Research is, of course, important to a number of you. We have a lot of exciting research. This is just, I grabbed like the last, so many funded NSF proposals that I saw. Lots of fantastic things across all sorts of areas, from disaggregated storage to quantum circuit compilation, everything in between. Next slide. And also, if you look at things like our output at CS rankings or something like that, you see in a lot of areas, we're just at the top or near the top. Everything we do, I think we do really well. Next slide. Education. Okay, next slide. Education's important, I think, for you. You've been getting educated for a while. We're gonna have to ask the next slide again. Thank you. That's at 2 levels. As a grad student, you think about like 500, 600 level classes. Those are like upper level undergrad courses or graduate courses, which are 700 level and higher. And one thing you'll face right away is, should I, take the 5XX level or the 7XX level? And of course, that depends on each of you. Sometimes people take the upper level undergrad because they want to shore up their knowledge in something. And then of course, sometimes you want to go into the paper reading, graduate oriented courses, PhD oriented even, which are 700 level courses, and they're all great. And what are cool about the 700 level courses in particular, like when I'm running a systems course, which is my area of expertise, you get to do like a little research project often within them at the end of the course. So you get a sense of the flavor of research in that area. So of course, all things are good there. Okay, next slide. Next slide again. Sorry, that apparently does an inverse animation. People are a great reason to come here. Let's do a next slide there. Okay, our people are great here, and that's a lot of different people. You learn from everybody that's around, professors, students, staff. And so, figure out how to work with all those people. Of course, sometimes you think about the faculty and professors because those are whom you take classes from, but of course you learn a ton from the students you sit next to. So, your future classmates may be in this room, and always take time to try to learn from them too, because each one of you comes with different backgrounds and knows different things. And there's nothing better than sitting next to someone, seeing how they do something and saying, oh, I could do the thing better than I've been doing it. And I think our people here are great. This is an example of our faculty being great. Again, just kind of scan through the last so many awards people got. There's a bunch of awards from things like, distinguished faculty awards to some test of time. Like a bunch of our faculty won these test of time awards on papers, which meant you wrote the paper 10 or 20 years ago, and people still today say that was a really important foundational paper, and all sorts of things in between. Next slide. Our faculty are great. That's them. And you can see we're growing. That means those blue boxes eventually will be people too. So we've been hiring like crazy. We're in a spring hiring season right now. We're interviewing about 35 faculty, potential faculty members to hire, 4 or 5 more. So we're in a time of incredible growth. Next slide. And then we have great staff. As you met Molly and Angela, of course, they're fantastic. Here's a list of some other folks that you may interact with. We have fantastic staff here. They, of course, make sure everything actually runs here and works, and do so much more for our department. So please get to know them too, and your time here to the extent that you can. Okay, next. Great people. Great students. Too many students to show their pictures. We have hundreds of graduate students here. We have thousands of undergraduates. Some of you, probably a couple of you undergrads here. How many people are undergrads here? Yeah, fantastic. So I have to say you're fantastic, but actually you are. So fantastic undergrads. Too many to show their pictures, but I'll show a few pictures of alums on the next slide. Some alums of ours. Oh, back one. Yeah, here's some just randomly chosen alums. Sarita and Joe are the 2 academic ones I chose, fantastic alums of ours who are professors at great institutions. And then Judy Faulkner and Colin Huang. Judy founded Epic Systems, which is the software that actually runs on most of the hospitals of this country. And then Colin founded Pinduoduo, which I recently learned ships more packages daily than Amazon. So kind of impressive alums. You have some work to do to live up to that, I guess, but we expect you to do it. Okay, fantastic. Next slide. Okay, school. Let's go to the next slide. Yet another reason to come here. We formed a new school. So you've applied to the Department of Computer Science, but we formed a new superstructure on top of ourselves and statistics department and a department called the school, which is the iSchool. It's called the school. So we're in the School of Computer Data and Information Sciences, or CDIS, I often called CDIS. And really the point there was to do a couple things to enable computing and data it's just become so important in society. And we really need high-level leadership on campus to help with that. So it's one of the main reasons we formed the school. Tom Erickson is our fantastic director. He's an alum, actually. And it's catalyzing a lot of larger initiatives and connections with other colleges and so forth. It's just really advanced a bunch of things. We already have over 4,000 students across the 3 departments. So we're kind of a big entity. We're like almost as big as like the B school or even engineering. And really, it's the beginning of the process of this new school. And I'll talk about one concrete thing that we're working on together, which I'll go next slide. Next slide is architecture. Next slide is a new building has begun. You may have noticed there's a big hole in the ground over that direction. So don't walk into the hole. And by the way, when I made a slide, I didn't think I made that groundbreaking has become quite that big, but it is exciting. So let's look at a few pictures of the upcoming building, which is going to house the entire CS department, as well as the statistics department, the I school. Also, there's an American Family Data Science Institute, and then half of a department called the Biostatistics and Medical Informatics Department, which has a bunch of people who do AI, but is connected more to like, the medical profession. They're going to all be in this building. We'll all be in this building together. You can see, so that's where the hole is right now, right? And you can see the building up to the upper left is where we are right now, right? That's the Wisconsin Institute for Discovery. And then you can see over on the bottom right there, that's the psychology building, who are all mad at us for building this new building next to us. So if you see people in the psychology department, be nice to them because they have to deal with this building getting built right next to them while they're in their old crummy building. My apologies, psychology friends. And then you can see what's a very cool building. It has like a bunch of outdoor spaces, like between the psychology and new building. You can see there's a courtyard. On the 3rd floor, there's this outdoor space right there. And then on the very top 7th floor, there's also a beautiful outdoor space. Let's go to the next slide. This is an outdoor view. This is a view kind of looking south. The Discovery building we're in is on the right. If you can see that, this is the new building on the left. And then you can see our old little sad CS building poking out, sadly looking over this new building. You can see it's kind of looks morose over there because it understands that we're moving out of it. Next slide. This is like a lecture hall, fantastic, beautiful rooms to get, you'll take a class. Next slide. And then this just shows how open and beautiful this building is going to be, right? So there's this, throughout the middle of the building is what you might call an atrium. But there were some campus people that said we can't have an atrium in this building. So we called it the heart of the building and made an atrium. So there's this thing called the heart of the building, which just is a kind of a winding open space with stairs all around. And you can just see how open and accessible it is. You'll see people across floors, on your floor, et cetera. Just a beautiful new space that if you stay here long enough, you'll be a part of. So groundbreaking has begun, as I mentioned. It takes 2 years to build a $250 million building, it turns out. But you'll see its progress. And if you stay, like A, you do your master's slowly, or B, you do a PhD, you'll 100% be moving over to this building. Okay, next. Summary, fantastic. Let's summarize. I think you have to flip a bunch to get, you should come to Wisconsin. There's a lot of reasons: place, history, research, education, people, school, architecture. And that spells the acronym FREPSA. But then I was looking at that. I'm like, I can do better than that. I can just rearrange it, which is rearranged. What word can I get out of that? Anybody guess? Oh, we got to do it again. Now let's try again. Perhaps you should come to Wisconsin. So I'm trying not to be too pushy, but that's pretty good. I got a word out of it. Anyway, so I think you can hit one more next. One more next. Yeah, anyhow, I forgot. It was just, it's going to be a long morning. Perhaps you should come to Wisconsin. So anyway, thank you very much. It's my pleasure to greet you all. I hope you have a great time today. And I hope you have a great time in figuring out, your next stage of life. It's an exciting moment to have graduate school in front of you. I certainly remember so fondly thinking back to those times of, you're thinking about, what am I going to do next? What am I going to learn here? And each class and each interaction with, some research area is so interesting because you just know a little bit about it, right? This end of undergrad, one of the reasons I went to graduate school was this sense of, I know a little bit about a bunch of things, but not that much about anything. And then coming to graduate school, you hope to deepen that knowledge. And of course, what happens in any educational process, the more you know, the more you realize how little you know. But I hope you can do that process with us. So thank you. And I hope you have a great day. Okay, thanks. Yeah, that's
Sorry. Okay, let's leave the slides up here. I should just say next slide. That's what you know. Let's quickly. Oh, yeah. So the mic also, yeah. Okay. Good morning, everyone. Hopefully you guys had a nice breakfast. And yeah, as Ramji said, we are a really exciting school. And now I think you're going to hear about different research groups and what we work on, and sort of just different faculty that we have here and different research collaboration opportunities that you might have when you go to school here. So, so the slides already began. But so I'm going to talk about the theory group that we have at Wisconsin. And first, let me explain what theory is, or theoretical computer science. It's basically a subdiscipline of computer science itself that focuses on mathematical sort of just rigor and sort of just mathematical foundations of computational and algorithmic processes and interactions. So this is a statement that was kind of written up by a group of 10 Turing Award winners about 5 years ago. And they kind of summarize what it means to be a theoretical computer scientist, or what it means to study theoretical computer science. And moreover, in theoretical computer science, the questions that you want to really ask are, next slide, that what does it really mean to compute? I mean, it's computer science. It has the word compute in it. So what really it means to compute something? Moreover, what is really computable? That kind of defines the questions that's kind of, is below everything that we study in computer science. The P is equal to NP question. That is based upon the definition of what computing is and how efficiently you can compute things. Next slide. Moving around, I don't know, it should have looked a little bit nicer, but moreover, just the study of understanding what computation means and how to sort of just mathematically analyze it, it has resulted in many new disciplines within computer science and also outside of computer science. Disciplines that didn't exist about 40 years ago, such as learning theory, cryptography, security, quantum computing, economics, computation biology, geometry, and much more. And these are some just short sample of the disciplines of the topics that have come out of studying theoretical computer science. And on the next slide, the importance in TCS is basically the emphasis that we put on mathematical rigor and techniques that we use to sort of formalize all these questions and try to ask them in a more mathematically sound way that they basically make sense. And they are not sort of just words, but they have like a mathematical framework around them that you can not just argue, but kind of prove in a sound way. So on the next slide, let me actually just tell you about the historical roots of TCS. So you already might have heard about Alan Turing, Gödel, Alonzo Church. He was actually the advisor of, I think, almost all of them. Emil Post, Stephen Kleene, that you actually heard from Ramsey about. So Stephen Kleene, all these folks are, I mean, the big people in computer science, and probably, I think now, you know, they're actually the founding figures in TCS. And there are tons of Turing Awards that have been awarded for people who have studied theoretical computer science. And that's just a list that's kind of growing. Even the Turing Award winners that we might have next year, they might again be theoreticians. So who knows? It's always like a battle. But it's perhaps the largest, perhaps just using the word that Ramsey found on the previous slide, but perhaps it's the largest group among all the different sub areas that you can define in computer science. So the maximum number of Turing Awards that have been awarded so far are in theoretical computer science, because that's really the core, the heart. Everything else has kind of spawned out of studying what computation means and how to do it efficiently. Even all the questions that you asked today, they're kind of typically trying to make something more efficient or trying to come up with a different procedure of solving a particular problem. All those questions have their roots in theoretical computer science. And on the next slide, let me actually just tell you that we have a theory group here that kind of works on a wide variety of problems in TCS. And here are the faculty: Eric, Ginny, Elias, Dieter, Christos, and that's me, Rishabh. So let me, in the upcoming slides, just give you a brief overview of the topics that we actually study. But before going into that, let me tell you about our students. So we have a really big student group, and also we have a bunch of postdocs that work within our group. So we have around 15 students right now. It kind of changes every year. Just now, some of you might join our group, so the number is going to change, and we hope that's going to be a bigger number. And our students have kind of gone on to different places. They have been faculty in academia. They have been in industry, sort of just led research labs. And many of them also go on to do postdocs at very different places around the world just to pursue their academic dreams. And those are the kind of opportunities that kind of will be available to you if you join the theory group here, because that's not only going to sort of just teach you what TCS is or just let you do some research, but kind of open doors towards a better or brighter future where you can be independent researchers, be in industry or in academia. So on the next slide, let me actually tell you about some of the research topics that Professor Eric Park, he kind of works in. So his main area of research is basically algorithms and in number theory, algebra, and combinatorics. So what happens in this area is that you typically use math tools that deal with number theory, also with algebraic geometry, and kind of use tools that are developed in those particular sub areas of mathematics and computer science to kind of solve many interesting problems. So let me show you some kind of couple of interesting wins that Eric has had over the last few years. Actually, I mean, he's one of the oldest, he's one of the longest tenured faculty that we have in our department. So I can't really summarize all the work that he has done, but these are sort of some quick samples from his long, more than 30-year-old career where he has done extensive work. He was doing cryptography research before I was even born. So that should tell you how the amount of research he has done in his entire career. That's not trying to date how old Eric is, but he has done really great work. For instance, so there's just this work on trying to figure out that bad seeds are exponentially rare. What that means is every algorithm is typically kind of has a failure probability that that algorithm might not work. So really, it's like an old foundational work that kind of told us that for a lot of interesting tasks that we kind of regularly do, such as trying to figure out whether a number is a prime number or not, finding bad randomness or bad inputs that give you an incorrect answer, that's extremely rare. Just figuring out this particular simple looking a mathematical statement, that was really hard back in the day. And Eric was involved in sort of just answering those types of questions. So in the next slide, let me tell you more about what Ginny has worked in. So Ginny is basically a complexity theorist, and he works mostly on problems related to dichotomy theorems. So dichotomy theorems are kind of an interesting way of proving something is either in a class P or an NP complete. And it's a very broad way of sort of summarizing what he works in. But you might be thinking, okay, hey, there are just two classes, P or NP. It turns out there is actually an intermediate class called NP intermediate that sticks around between P and NP, and that only exists if P is not equal to NP. That's where something kind of we use cryptography. Cryptography is that intermediate class. It's like this magical class. But what he really is interested in, can we actually sort of just figure out problems which are in one of those classes specifically, just maybe sort of just have interesting theorems about that. And moreover, I think he has done great work. And on the next slide, you'll see that he has won one of the really honorable prizes in TCS and computer science more generally, the Gödel Prize. I mean, it's named after Kurt Gödel, and you might have heard about Gödel's incompleteness theorem. So it's a really big deal. It's not awarded if you, it's awarded for really foundational work. And he's also won the Fulkerson Prize. So people might have heard about algorithms in graphs. So you might have heard about the Fulkerson algorithm or those types of things. So again, these sort of just amazing prizes have been awarded to Ginny for his work on complexity theory. So the next slide, let me sort of just quickly tell you about Elias's work. So Elias is a learning theorist, and he works on the foundationals of machine learning. So at this point, people might be wondering, hey, machine learning is more like an applied science. How does it connect to theory? I mean, well, the birth of machine learning was actually in theory. It's really a learning problem. You can kind of phrase any machine learning problem as kind of like a learning problem. Typically, when you are trying to build a machine learning algorithm, the goal of the algorithm is to figure out a model or a function that kind of generates inputs and outputs, sort of generates outputs from certain types of inputs, kind of like take an image and try to label it. So that function, learning that function can be phrased as a mathematical sort of just like an algorithmic task. And that's what learning theory is all about. He has sort of just done great work in supervised learning, high dimensional statistics. And on the next slide, you might sort of just see even more questions that he's interested in, specifically in algorithmic statistics. How do you perform some type of estimation and hypothesis testing? That's very important and like a foundational sort of just question in statistics. And also sort of it has many applications in building reliable machine learning systems. So that's something I think you're going to also hear in Qasim's talk, that there are a lot of problems in sort of just using machine learning today. And that's because we don't have reliability. There are questions related to fairness, to sort of just adversarial examples, and all those things, the kind of those questions make, it's it's much better if you try to understand those questions at a foundational level rather than trying to fix a problem in an algorithm. Try to come up with better algorithms to begin with so that those problems don't arise. So all those questions are very important, and kind of this is where TCS comes into the picture. So on the next slide, let me tell you more about Dieter's work. So Dieter works in de-randomization. So I kind of quickly mentioned about the P versus NP problem, and that's really the problem that you want to solve, or one of the problems that you want to solve. People might have heard about, that's one of the, I think it's seven. It's one of the 7 problems for which you can get $1 million prize. I mean, technically you can get a lot more than $1 million if you can solve the P versus NP problem, because you can break all of crypto and then you can sort of just get all the money from all the blockchains, all the banks and everything. So that's great, but 1 million is more like a token money to say, okay, hey, that's a really hard problem. And so to solve that problem, there's a very interesting technique, or to sort of just maybe an idea or the entire area where we kind of understand, can we kind of de-randomize any particular randomized algorithm? It turns out answering those types of questions is very crucial and is very important in trying to understand the complexity of P versus NP classes. So Dieter has done great work in that domain. He's also worked into figuring out the lower bounds for the NP hard problems, how basically a randomized algorithm, what's the best thing that a randomized algorithm could do? How worse can a deterministic algorithm can do? Is there a gap? Is randomness truly needed in trying to solve problems? And on the next slide is just some more current work that he's involved in. He was sort of just telling me about some cool work that he was working on, trying to figure out hardness versus randomness trade-offs in certain interactive proofs. Interactive proofs is something that kind of I'm going to briefly tell you about towards the end of this kind of mini talk. But these are kind of very interesting objects that we actually use almost every day. They're kind of used in many of our digital communication, secure communication these days. So in the next slide, let me tell you more about Christos's work. So he's also interested in learning theory and computational statistics, but more broadly, he's also interested in algorithmic game theory. Game theory might be something cool. People might have seen a couple of movies about game theory. So I don't know what's the name of the movies, but maybe Beautiful Mind had something about sort of just a foundational question about Nash equilibrium and all those things. I think that's the movie. Or if I'm wrong, then okay. So I see a thumbs up. Thank you. My movie trivia might not be working that good, but in that case, game theory is like a really fantastic sort of just area, because you kind of answer these questions. On the next slide, you'll see. So there are a couple of interesting questions that you can ask when you sort of just working game theory, that how can you sort of potentially price different objects, and how would that affect the entire market? Because you have to not only formalize how to capture a market, how to capture a particular pricing, but also all those questions that deal about volatility. And these questions can actually be understood as more like theoretical questions in computer science. So in the next slide, let me actually tell you some of my work. So I'm a cryptographer. I'm also interested in computer security. And next, you'll kind of hear about more about security from Kasim. But what are my interests? I actually am broadly interested in any aspect of cryptography. If you want to do theoretical cryptography or sort of just some applied cryptography, there are some interesting questions. I work in quantum cryptography, post-quantum security, number theory, lattices, zero knowledge, obfuscation, succinct proofs, and moreover. And let me sort of just quickly end by telling you about some sort of just on the next slide, like a simple, cute object that we called batch arguments. So let's just do a couple of next slides. And then the goal is that there are 2 parties. Party 1, it has basically n inputs, and there's a fixed program P or a circuit C. And the party on the left, that's called Alice. Alice wants to prove to Bob that I have n inputs such that C of x1, that's I have n accepting inputs. So Alice can prove this by just sending all the n inputs to Bob. Now the question is, can you actually create such a proof pi without sending all the n inputs, by kind of just sending one input? And the properties that we need, just to make like the next slide, is that the proof should be succinct. It should not grow with the number n, the number of instances that you have. But also it should be the case that the verifier, Bob on the right-hand side, it should sort of just say, if there are no n accepting inputs, then just reject the proof. And there are tons of different applications that we can see on the next slide that go from certificate chains to next slide, to secure broader gateway protocols, to even blockchains on the next slide. So, and there are many interesting questions that you can ask about that not only can you compress information, but can you delete information? So it seems like typically when you compress information, there's no way to delete information, especially when you're having an exponential amount of compression. But in some recent work that I was sort of just working on, we were able to figure out a really counterintuitive way in which not only we can compress things, but kind of decompress and also delete information. And that's kind of very, very contradictory, but that's kind of where the magic of cryptography comes into the picture. So on the next slide, and let's just get to the next slide again. So there are many more reasons to work with the theory group beyond sort of just doing research with us. We kind of sort of just are interested in teaching many interesting courses. And I'm not sure what happened with not sure if you guys can see all the courses, but they're fantastic courses that we teach. And even if you don't want to do research in theory, it's very important to actually take a lot of theory courses because they build the foundational understanding of different subjects. Suppose you want to build a particular system and you want to formally verify by kind of building like a PL-based formal verifier. You need to understand how to actually prove something, how to come up with a soundness proof. And it's very important. We have tons of theory courses that you can get into. And on the next slide, there are many more topics courses that we also teach. So we are always happy to teach sort of just some new interesting topics that the entire student population is interested about. And yeah, that's all. So feel free to sort of just talk to us in any of the open houses and all those things. So next, Qasim is up.
Good morning. How are you? Welcome to Madison on this exceptionally cold day. It's usually not that cold. It's colder. No, just kidding. I'm Qasim. I'm assistant professor in the ACA department. I also have an affiliate position in the CS, and I'm part of the security and privacy research group. So the next, actually, I don't have 15 minutes. I have only like 10 minutes or so, but I'm going to scare you a bit and then try not to get you too scared. The nice thing about, you're going to be hearing lots of research today, and it's going to be very interesting. But what you should take out of this is that the more interesting research happens, the more interesting technology we're going to be getting, the more security and privacy problems we're going to end up at. So when you join our security and privacy group, you're not going to run out of research problems. So that's a good thing. Next. Now, security research involves understanding and improving the behavior of computing systems in the presence of adversaries. Adversaries are the most interesting things, or the most interesting entities that you're going to be interacting with when you're doing security and privacy research. And I'll give you a very simple example on machine learning. Next. Who knows machine learning? What machine learning does? Well, we should know because we interact with ML systems every day, right? And they're very cool. They allow us to do very cool things, right? You can recognize objects, you can do capture, it can solve captchas for you. It can do speech recognition, it can do lots of things. Any very recent application of machine learning? ChatGPT. Who has used ChatGPT in a course or to submit an assignment? It's fine, right? Yeah. Cool. But of course, what happens if the not so good people are using these machine learning systems or try to exploit these machine learning systems? Next. Okay, what's this? What's this? It's the cat, right? But the model says it's guacamole. How did this happen? So there's this field called adversarial machine learning, where people have discovered if you add some noise like this, and this is amplified noise, so the magnitude is much smaller, you get this, you add it to this, and then the model goes haywire. Scary, right? So how could this be very scary? Self-driving cars, next slide. Well, before we get to self-driving cars, we're gonna look at other examples to where adversarial machine learning can be, I wouldn't say useful, can be applied. Malware detection uses malware detection uses machine learning, right? So what would an attacker do? They would try to trick the model. They trick the model by changing the malware a little bit. How about spam detection? Same thing. How about voice recognition? So people have found if you just add imperceptible noise to the medium, you can trick the speech recognition algorithm into hearing something else. I'll show you a very interesting example in the later step. Next slide, please. I will get back to cars. So cars or any existing system has a bunch of sensors, right? They have cameras, they have lidars, they have all of these things. How do they reason about the world around them? They have to use algorithms and machine learning algorithms. But do they really understand what's going on? We'll see. Next slide. Of course. Next slide, next slide. Just go next. Okay. So researchers in our department have generated these very interesting stop signs. What's interesting about these stop signs? Next slide. Can you play the video, please? What's the video? Okay. So there should be a video that should be playing here. I'm not sure why it's not playing, but this is a stop sign over here, and this is a regular stop sign. And the model over here recognizes this as a speed limit sign. That's scary, right? Why? Yeah, I don't know why. Anyways, it's okay. So this is scary because the car will just run over, right? So, okay, next slide. Just next. Next. Okay. Okay. So one very interesting example of research from my group is speaker identification. Do you know what speaker identification is? Who uses Siri? Siri is personalized to your voice, right? So you say, hey Siri. If I say, hey Siri, it's not gonna respond, right? Okay, cool. Oh, it works. So we tried to see, like, how can we attack these speaker identification systems? And lots of work has been done, like, let's replicate the voice, let's do speech synthesis. I wanted to say, well, can we do that through a non-digital technique? And it turns out that you can apply digital transformation, analog transformations to your voice. I can trick speaker identification systems and then you can impersonate people. And the technique turns out to be, you can just use a tube. So by speaking through a specially manufactured tube, you impersonate people according to the models. I'll spare you the details, but so this is our setup over here, and this is the theoretical model, and this is what we actually record. And it turns out because vocal tracks are modeled like tubes, and you use tubes in special way, then you can impersonate people. Scary, right? Are you scared a little bit? Okay. So this is the part where I stop scaring you. Of course, our research is to prevent these problems from happening. And we do that in different themes. The first one is trustworthy machine learning. Then we look at data and sensor privacy, user authentication, decentralized system security, and human factors in security and privacy. So I'll go very briefly of some of the research we're doing those, and I'm trying to make it less boring as possible to you. Okay. So we have faculty in our department, so Patrick, me, and Sumesh. We work on how can we leverage domain constraints to make machine learning more robust. So let me give you a very simple example. A car is looking at a stop sign, right? Why should the car just use a camera? It can use a LiDAR. A LiDAR will give you a depth map. It will be an octagon. Would the speed limit sign be an octagon? No. So that's a domain constraint. So how do you apply that to make the algorithm more robust? We also worked on privacy choices and control. One very recent example is our recent analysis on the mute button and video conferencing apps. So what happens when you mute yourself on Zoom or WebEx? Does WebEx stop accessing your audio data? Of course not. Good. So that's what we discovered. We also work on next generation authentication systems. One example is from Rahul's research, where if someone wants to log in, but they put in a typo, can we develop a more resilient authentication system so that when you have a typo in your password, you still log in? And that requires some tricks in cryptography and applied cryptography, and Rahul works on this. And you have also fancy things that work with sensors as well. We also have research on preventing technology abuse. And we focused a lot on these dual-use apps that have legitimate purposes for tracking people, but then malicious entities can use them to track people, and that is something that would be very interesting to study. One of our newest faculty members, Ethan, is working on the problem called re-entrancy security. So in the context of smart contracts, which are just pieces of code that run on a blockchain effectively, someone just sends a request for $10. They get the request back. Now, this entity over here, the financial entity, should check the balance, send the money, and then update the balance, right? It turns out because of vulnerabilities in the code, they check the balance, they send the money, and then the attacker can send another request, check the balance, send the money. So is the balance being updated? No, because of this vulnerability. So what happens is that the money goes in and the bank is not keeping track of the balance. So it just drained all of the resources. And Ethan's research is how to stop this. So this is a list of the faculty who are active in this security and privacy research area in CS. You saw a little bit of Rahul's research on preventing technology abuse, some of my research on security and authentication and trustworthy machine learning, Somesh's research, Patrick's research. So what does Rishabh work on? You just failed your first exam. You just heard what he works on. What does Rishabh work on? Cryptography. Okay, some of you passed the first drop quiz. And you have other people who will also touch on security and privacy. Paul works on intrusion detection. Bart works on fuzzing and software assurance. Mike and Tom Raps work on trust management, model checking security. You're going to be hearing from Mike very soon. And Rishabh works on applied advanced cryptography, as you already heard. These are some of the security and privacy courses. Actually, these are all the courses that we offer. We offer a software security systems course, a computer security, introduction to computer security, security and privacy and data science, and advanced topics in computer security and privacy, which is cross-discipline ECE, and I'm teaching that course right now. And you have the crypto course over here, which is dark because crypto can be dark. It's not a problem with the slides at all. This was on purpose. Although this is the course number is 435, this is 500 level. Don't get too bogged down into the course numbers. Many graduate students take all of these courses. Okay? That's all I had. And please follow us on Twitter. We're not very active, but if some of you want to make this a more active Twitter account, please join us. Thank you.
Got to raise this up just a little bit.
Hi, welcome everybody. I'm Mike Swift. I study operating systems, or really sort of computer systems far more generally. Let me just make sure I understand this. So what I want to start off with is just sort of explain what systems research is. Many of you may have taken an undergraduate course or even a graduate course in operating systems or distributed systems. And there's sort of, how do operating systems work today? And the systems research is really, why do they work that way? How should they work in the future? So a good quote about this is Edgar Dijkstra. He was sort of a pioneer in early operating system design. He was sort of one of the first people to systematically study concurrency. What happens when you have multiple things happening at the same time? How do you reason about that and control it? He invented the idea of semaphores that some of you may have run across using. Some of you may have learned to hate them. He also did a lot of work on program correctness. How do we make sure that our programs actually do what we want? And he has a great quote that sort of explains why systems research is the thing. And he says, the intellectual level needed for system design is generally grossly underestimated. I am convinced more than ever that this type of work is very difficult and that every effort to do it with other than the best people is doomed to either failure or moderate success at enormous expense. And this might explain perhaps some of the operating systems you've used. Something about who is creating those, some of those. I worked at Microsoft, by the way, for 8 years, so I feel a little privileged to talk. Butler Lampson is another luminary of operating systems. He worked at a place called Xerox PARC that did a lot of early work on graphical user interfaces. They invented Ethernet and local area networking and laser printing there. And he sort of wrote a seminal paper on some of the complexities in operating system design. Designing a computer system is very different from designing an algorithm. The external interface, this is the system calls, is The requirements is less precisely defined, more complex, and more subject to change. As our applications change, as our hardware changes, that interface has to change. The system has much more internal structure. We've got a huge amount of stuff happening inside that has to interoperate, hence many internal interfaces, and the measure of success is much less clear. It's harder to say this operating system is much better than this other one, given the wide range of things we want them to do. Leslie Lamport, another Turing Award winner, operating systems, distributed systems person, was writing about the complexity of distributed systems and said a distributed system is really one in which the failure of the computer you didn't even know existed can make your computer unusable. I'm sure many of you have experienced things like that. For example, when the server holding everybody's password goes down and nobody can log in. So operating systems has a pretty lengthy history of impacting the world. Unix and C were invented at Bell Labs by a bunch of systems researchers. Other things like local area networking was invented by systems researchers. The mouse, window-based interfaces at Xerox PARC kind of came out of systems research. Linux that we use today to power data centers and Android cell phones is really a direct descendant of the design ideas of Unix. There's a huge amount of work in the systems research around how do we manage distributed storage. It's great to have files on your computer, but it's a lot more useful when you have storage that you can share, when you can store a lot more data than you can fit on one computer, and when you can make it available and reliable across the entire planet so you can get to your files wherever you are. So an early piece of work here was this NetApp waffle system, which sort of showed that you can build a storage appliance that you can kind of plug into your network and can reliably and securely store data. Another big impact of operating systems research is virtualization. This is the technology that powers cloud computing, and it came out of a bunch of systems researchers at Stanford who the original product was really showing how can you run multiple operating systems on a single computer by creating a software version of your hardware and processing platform that you could then share, which would allow you to run Linux and Windows and Mac OS or DOS or anything else you wanted on a single machine. This was also, there's a host of other systems research projects. The Zen virtualization project from the University of Cambridge was the basis of Amazon's cloud computing project early on. Docker is another form of virtualization, which is used for packaging applications for easy distribution. So there's a huge amount of work in these areas on how do we build better virtualization systems, making them more efficient, making them more compact, making them faster. As I mentioned before, a huge area of systems research is really around storage. And one of the big things there is how do we scale to the very large? If we are building internet services where we want to organize information for the planet, you might want to have a copy of the entire internet on your local machines to analyze. So one of the things that systems researchers look at is how do we build ways of storing and accessing petabytes of data? And then furthermore, how do we write programs against that? We don't want to just write a program and have to individually launch it everywhere. We'd like an easy programming model that lets us access all the data where it is and analyze it and make sense of it and aggregate results without having to have programmers manage everything. So Google has done a lot of work in this area with the Google file system, which is now there's an open source version available for researchers to use called HDFS, and MapReduce, which is a programming model. And there's now many open source versions of similar things that researchers do a lot of work with. So this scale that we have from being able to build these big storage systems has also allowed us to build sort of many more ways of working with lots of data. So big data analytics has sort of taking over the world at this point. There's, data science is becoming a big thing here and elsewhere. And part of this is enabled by having systems platforms that can organize all this data and then run analytics programs like Spark, where you can actually do complicated analyses of, huge amounts of data. This is also critical for machine learning. You've heard a lot about large language models like ChatGPT from OpenAI. These require huge clusters of computers that are processing terabytes of data, training billions of parameters, and there's a system behind that that has to do this all efficiently and at scale. So that is the kind of thing that systems researchers work on. So most of what I was telling you about was sort of the past successes of systems research. Lest you think that systems research is dead, and I will tell you there are famous people in computer systems who said 20 years ago operating systems research is dead. Fortunately, he was wrong. There's a lot of stuff going on. And so really the way to think about this is that systems really is the layer between the hardware and the applications. What this means is that if applications change, We go to have machine learning if we want to scale up to the whole planet instead of to a single room full of people. Our systems need to change to handle that new application load. If our hardware changes, if we have new storage devices, new computing devices, we have multi-core processors instead of uniprocessors, then our systems have to change. So for example, just looking at what is happening now, sort of currently going on, we have new workloads like self-driving cars that Gassem was talking about. These are cars that are ingesting huge amounts of data in real time from multiple sources, integrating it, trying to make a decision and steer your car with millisecond response time. This takes a computer system to sort of orchestrate all these inputs and guarantee you can respond quickly and not drive into a stop sign. We also can look at data center hardware. There's new ways of organizing your computer systems. For example, switch attached memory lets you have like a single server with memory that you can share across a whole rack of machines for more efficiency. That takes new system support to decide how do we use and share that. There's new memory technologies like non-volatile memory that doesn't lose contents when it fails. We then have to think about how do we actually program this? What if we're in the middle of updating something when we have a power failure? And then finally, we have all kinds of new compute technologies. Our computers now are not just CPUs, but they have GPUs. They have tensor processing units for accelerating machine learning. They have FPGAs for accelerating, any kind of specialized circuitry. And all of this takes some system support to make it efficiently available to applications. So this is the group of people. Unfortunately, our pictures are a little bit out of date. So there's Remzi and Andre Arpachi-Dussault, who formed the Arpachi-Dussault group, and their work really focuses on file systems and storage performance and reliability, which we'll talk about a little bit more. Bart Miller, his work focuses on debugging supercomputer applications, both for correctness and for performance analysis. He also does a lot of work on computer security, as you just heard. My work really lies at the intersection of systems and everything else, systems and security, systems and architecture, systems and networking, systems and databases. I sort of like to look at that boundary and sort of see how these areas can cooperate and build better systems. And Shivram Venkataraman is looking at big data and machine learning and data analytics and looking at how can we build systems that are more efficient, that can sort of make these workloads run much better on less hardware. So lest you think we are some podunk school in the Midwest, we actually are pretty good at systems research. So this is data from CS Rankings updated last night. It is kind of a hack. It basically just shows who is publishing papers in systems research. And this is looking at the top 5 systems conferences and looking at who publishes papers. Now, we're not number 1, but we are number 2. And we are doing this with only sort of 12 people working in this area. And we're above other schools that might have a lot more people working in this area. And this is not to say really that rankings matter that much, but what it is to say is that we are very productive and we're effective and we have a lot of impact in this area. And it's widely recognized that Wisconsin is an excellent school for systems research. So, what are the things we're actually doing right now? This is a short list of recent research papers from the past few years. I'll give you a minute to look at it to see what catches your eye. There's work on computer security, Java cryptographic APIs. We have building systems for graph neural networks, cluster scheduling, persistent memory, file system design, other kinds of storage devices. So we really span a large range of different kinds of systems research, that sort of fits a lot of different interest levels. So another big question is, where do our students end up? You may all have different goals of what you want to do. We have students who go to become professors. So Aishwarya Ganesan and Ram Alagappan went to UIUC and started this year. Xiaozhu Meng is at Rice University. These are just the most recent people. We also have people at University of Texas, University of California, San Diego, a bunch of other schools. A lot of our students go into industrial research at sort of the big companies, Facebook, Meta, Google, Microsoft, Intel, IBM. We also have students who go off to do startups. Very often they will go work at a big company for a while, get some more skills, find some people, or find a small startup that catches their eye and go work there. We also have people who've gone into government labs, particularly people from the supercomputing world who are interested in working on those incredibly big high-performance computing applications. If you want to see more details, there's a website, madsystems.wisc.edu, that has more information. So I'm going to talk a little bit about current projects. And the point of this graph is really to sort of show there is sort of a whole set of different parts of a computer system, from applications to sort of the cluster scheduling distributed systems layer to the operating system and hardware layer. And we have people working all across these different boundaries, sort of looking at the architecture operating system layer, which is sort of where I work, looking at the application machine learning systems layer, which is where Shivram works, looking at sort of the distributed systems operating system layer with storage, which is where Remzi and Andrea work. So one big major area of research here is looking at storage systems, sort of broadly. And sort of two things that have sort of long had interest here. One is non-volatile memory, which I mentioned before, and really looking at, if we have this new technology, how should we use it? How should programmers write applications? If your data doesn't go away when you restart your application, maybe that's a bad thing because you actually had errors in your data you need to recover from. It might be a good thing because now you don't have to write your data out to a file. So how do we make that available to applications? Broadly, Remzi and Andrea, Arpachi Dussault, do a lot of work on reliability and consistency of storage systems. So if your system is going along, you get a power failure, you would like to make sure that when the power comes back, that all of your data is there. It turns out modern storage systems actually don't do that very well in many cases. And so they have done an incredible amount of work and developed some really neat techniques where they will sort of like artificially make things fail and see what happens in a very thorough way to understand just how good our systems are. Shivram Venkataraman does a lot of work on machine learning. He has built a lot of systems to sort of accelerate machine learning by doing a better job getting data from where it is sitting to where it needs to be, to scheduling things so that they run more efficiently, and both on a single node and on a distributed system. There's a bunch of works on cluster computing of various scales. So Shivram, part of his work on distributed machine learning, looks at stream processing across the cluster. Bart Miller does a lot of work on performance and debugging tools. So for example, suppose you're writing a program on a supercomputer that runs on 10,000 processors, and you want to get a stack trace to see what's happening. What does it mean to take a stack trace across 10,000 machines? He has tools that can do this that sort of give you a really great representation of what happens. Another example is understanding performance problems. He found that there was a supercomputer using GPUs, and they're actually compiling with the wrong compiler flags, and their code is running half the performance it was supposed to be, and nobody knew this was happening. So there's a bunch of like low-hanging fruit of how do we make sure our systems are doing what we think they should be doing, that his work entails. So hopefully I've intrigued you. A bunch of us are around this afternoon. You can come talk to us. We have an open house this afternoon from 2 to 3:30. It should be on the schedule. So our students will be there and can tell you more about all the work that's going on. So thank you all. And I hope I have piqued your interest, and I hope to see some of you later today.
Good morning, everyone. Welcome. So I'm happy to talk about the networking research. So in my opinion, networking research is about building fast, efficient, secure, reliable network systems and protocols for different kind of skills. So in terms of fast, usually what we mean is like we try to maximize performance to achieve the physical limits of the communication medium. We not only consider the performance in the unloaded case, but we also consider the performance when the link is fully utilized. And by efficiency, we consider efficiency in terms of gigabits per second or gigabits per dollar. The key thing here is that we want to understand the cost of data movements, and we want to consider this problem in the context of multi-tenancy. And in terms of secure, we want to minimize the attack factor. We also want to design the fast prevention or detection techniques to ensure we are able to make the system secure. So nearly 40 years back, when we designing computer networks, we introduced virtual circuits or virtual channels to providing physical isolations for networking systems. However, what we found is like when we introduce such kind of techniques, it will jeopardize efficiency a lot. As a result, if we're looking at today's communication medium, they are mostly shared. Therefore, one problem that we always trying to consider is how to minimize the interference for concurrent transmissions. And finally, in terms of reliable, we are trying to make sure the system is fully available and also try to minimize the downtimes. In order to do this, we want to develop tools to providing fast troubleshooting. So we consider networking systems at different kind of scales. This can be skills in terms of SOC. We want to consider how can we design communication systems for different hardware entities on one SOC board. But we also consider larger scale, for example, for radio access networks, for IoT device, for rack scale systems, cluster scale systems, or even data center scales. This is kind of the overall picture for networking research. And usually the networking research is driven by three factors. So the first factor is new applications. There are two perspectives here. One is we want to find new capabilities of computing systems so that we translate them to primitives and enable new applications. Some new applications such as embodied sensing, or some applications like battery-free communication. So this is one aspect. The second aspect is that we want to build communication substrate for new applications. So one typical example today is like service mesh has become a really popular communication primitive or like programming primitive for you to deploy applications in the public cloud. Today's service mesh is enabled by RPC-based applications go through today's traditional networking stack. Therefore, you will see lots of overhead. Now, the question for us is like, how can we design new communication substrate to maximize the performance for service mesh when deploying in the public clouds? So this is one type of driving factor. The second driving factor is new hardware. So when we're talking about new hardware, in our case, there are two kinds of hardware. One hardware is purely networking fabric. For example, we have programmable switch, we have SmartNICs, we have networking attached accelerators. These kind of new hardware providing us the capability to do per packet communications when we're moving packets. As a result, it will enable in-network communication. So this is one kind of hardware we consider in our domain. There's another type of new hardware is compute and storage device. So we have seen memory fabrics, which we are able to develop directly integrate standalone memory device into a cluster. We have seen Ethernet attached FPGAs have been hosted in rack scale systems. Now the question is like, how do we design the communication substrate to support this kind of new commutation device? So this is kind of another driving factor. And the last driving factor is new experience. So in the past, we have really built lots of computer networks. However, what we have learned so far, like what kind of experience we have been learned so far in order to manage our existing network better or building new network better. So there will be two things here. One is like we want to exploring the experience for existing networks by doing network management. And then another perspective is like we want to enrich our toolbox. For example, there are new techniques proposed from like programming language or from algorithm, from machine learning. They providing us better tool utilities for us to investigate what happens inside the network. And by learning from this insight, actually what we can do is like we can manage our networking better or building the network, the next generation network better. So this is the third driving factor that will be used in the networking research. So the networking group at our department have three faculties. Professor Paul Bufford is working on internet measurement, security, and data science. And Professor Suman Banji is working on wireless mobile systems and edge computing, and majorly working on networking-based hardware accelerations. So in the next few minutes, I will talk about each of us in a little more details. So Professor Paul Bufford is majorly working on network measurement. If you're looking at the three driving factors, he's majorly taking the third driving factor. So the key theme is trying to improve performance and resilience and expand services on the internet. The key methodology here is empirical. There are three major steps. Firstly, we want to gather data from existing systems, and then we want to apply a range of data analytics techniques. And finally, we want to build new systems. So he has a local testbed called Wheel, have a bunch of racks in the system, so holding a couple of local networking systems, networking infrastructures, but he also collaborates with a bunch of folks across the country to get a large scale data management. So I'm briefly talking about his two recent projects. So the first project is accessing internet networks. So the key question this project trying to answer is what is the impact of climate change? So as two examples, for example, we have seen the sea level rise. The buried optical fibers in the coast area is at risk. And we have seen wildfires happening every year, and the cellular tower infrastructure is being impacted in the US West and South. Now the question is, what is the impact? Is this only impact reliability for us to build the infrastructure, or it also impact the performance? So a key study from this project is trying to answer these questions, but simultaneously, we want to gather new insights about the next generation infrastructure. For example, if we want to design the next cellular tower, where do you place? And where do you place? You can take advantage of considering the factor from environmental change. So that's one major project. So the second project his group is working on is the internet vibration sensing. So the ground motion and structure monitoring has become a really critical capability for public safety and security. So one big observation that his group have for this project is we already deploying our existing internet infrastructure. Can we really leverage the existing infrastructure to do vibration sensing? So one idea here is trying to looking at the capability from existing infrastructures to looking at whether we can use tools to analyze the sensing capability. So his student, Joe, has deployed a testbed in our campus and built an initial study. So basically what the study shows is like, by using some laser platform, you are able to understand the sensing capability from existing optical fibers. And then the next step is how to using that to integrate into the ground motion and the structural monitoring tasks, and also how to improve the accuracy for such kind of capabilities. So if you are interested in that kind of research, feel free to talk to Paul and his students. And Professor Suman Banerjee is working on application-driven research, mostly following the second driving factor. And here, in the past 20 years, his group has operated their own 5G networks. They have their own TV wide space networking systems, own lots of wireless-based testbed. And he has working with the metro stations to get the wireless infrastructures built into the metro bus between Madison and Chicago. One project, for example, he's working on following this mobile sensing and edge computing is the driver analytics. So for example, when you're driving on the road, you will always have this kind of questions like where is my speed at different locations? Where did I brake too hard? How do I do this? So in this project, what they did is like they kind of build a small tracker integrated into the driver and then offloading that data into some systems developed at the wireless station, and then outsourcing the analytics task to the cloud. As a result, they build this map-based analytics capabilities so that you can answer these kind of questions. Another project is regarding healthcare. In this one, particularly, is the Power Job project. So what they did is like they kind of build a small SoC board, which is extremely low power, and integrate into the wearable therapy tracker. And then they build an edge analytics platform running on either Raspberry Pi, this kind of small platform, or local edge server, and then outsourcing the data into the cloud to get analytics. As a result, you can get some insights about what's happening inside the systems. So this is another project he's working on. So his group has focusing on another two directions recently. One is a satellite network, another one is space IoT. So if you are interested, feel free to talk to him or his students on these two directions. And finally, brief talk about our group's efforts. So we have mostly working on rack scale composable infrastructure. So what does this mean? So there are usually two ways for us to build racks. One is hyperconverged. So if you're looking at hyperconverged infrastructure, what you did is like, let's get servers from all the server vendors and then pile them up using the existing Ethernet switch fabric connecting everything together. So this is one hyperconverged way. The second one followed into this disaggregated case that we not only want this hyperconverged, we not want all the server nodes to become the same. We want them to become different. Some of them will be the GPU server. Some of it will be FPGA servers. Therefore, we can provisioning the cluster in terms of a bunch of heterogeneous nodes. However, in these two kind of approach, fundamentally, the computation and the system is holding by servers. So one big thing that in our group is trying to use new high bandwidth and specialized cluster interconnect to build a composable infrastructure. So what does this mean? It means that we want to remove server from the systems and using the cluster interconnect directly to holding the device directly. And the key benefit for us here is that you don't need to consider server anymore. You are able to scale the systems in any way you want on demand. And in particularly, we consider accelerators, we consider programmable switch and SmartNICs, and we connecting memories, DDR5 and HBM, or QLC, PLC, or Xenon SSDs into the system. And all these kind of storage, compute, and memory devices is held by this cluster interconnect. But what does this fundamentally mean? That's looking at this diagram. This is a prototype that we recently built, which is a routable PCIe fabric. Traditionally, when you want to holding a PCIe device, you have to put the PCIe device into your local server. And what the capability for this testbed is, we are actually enable PCIe to transmit directly over the wire to another box. So if you look at the system on the left diagram, here it is a traditional server and it's connecting to an end host adapter. And then we have this standalone PCIe switch connecting to the adapter. And on the other hand, we're connecting to this standalone chassis. So if you're looking at this chassis, nothing there. There's only power and additional specialized SoC board, which is able to hold all kinds of devices. So in this case, suppose you want to adding more GPUs, adding more FPGAs, or adding more NVMe SSDs, you can directly put things into this standalone chassis, and on the server side, nothing is being changed. This enables us to get this on-demand scaling and also providing us the consolidation capabilities. So this is one testbed that we built recently. Now the question probably you will have is like, okay, you have something like this. What does this mean? Basically, this requires us to rethinking the control plane and data plane when building application systems under such composable infrastructures. So as a simple example, like if you have something like that, you want to enable some kind of distributed applications, what is the communication substrate in this case? And how do you integrate your communication substrate into your application? And what is the limitation? There is cross PCIe communications, but it adds additional latency compared with local PCIe. Then it basically means you have to build techniques to hiding the latency. So regarding this, our group has been focusing on three different directions. One is like we want to looking at memory fabric. So routable PCIe is one kind of memory fabric. There are additional, such as the SQL-based systems, which is something we also built in the group. The second theme is we're looking at programmable disaggregated storage. And finally, we're talking about is program network, SmartNICs, and program switch. So these are the three projects that we are working on. If you are interested, feel free to talk to us. So today I'm talking about a bunch of projects that we have been working on and we are going to working on. Hopefully, some of the project we can working with you together in the future. So we have meetings, one-on-one meetings this afternoon and on Saturday. Okay, that's it. Thanks.
Okay, that's okay. All right, can you all hear me? All right, good morning. So today I'm going to be presenting on behalf of the Computer Graphics Lab, and let me just make sure that my controls are kind of like set up properly over here.
Okay, so we're going to be talking about visualization, simulation, robotics, multimedia, and I have lots of visual material. So, it's going to be a little bit like drinking through the fire hose, but I'll try to walk you through as quickly as possible. So, who are we? Mike Leisher has been here for more than two and a half decades. Yesul Kim is there we go. Perfect. Thank you. Yesul Kim has been with us for the last 3 years and doing visualization and robotics research. And I have been here for 12 years now, and my interests are in physics-based simulation and visual effect-oriented graphics. So I'm going to start talking about Yesul's research. She works to make visualizations accessible to people with visual impairments, and she incorporates a modeling of people's own interpretations of visualization into the modalities that she delivers. A good example of that is aspects and considerations about accessible visualization. To put it plainly, how do we best present data to people that have challenges in seeing, in terms of providing alternative text that assists visualization, focuses attention, and makes delivery more effective. As an example of tools that she uses, that includes making tabular data more accessible by developing browser plugins in order to both detect and provide fixes to accessibility issues, and also help users cope with tasks such as understanding merged cells, missing values, and those types of visual elements of data. And much of this functionality is delivered through browser plugins that help detect and fix those accessibility issues. And some of her newer projects have to do with accounting for people's own beliefs and like biases in the way that they interact with data, and ensuring that the best possible interaction between the two can be struck in order to have the best possible delivery. Then I'm going to move on to my colleague, Mike Leisher. So his research spans, roughly speaking, human graphics interaction, human robot interaction, and human data interaction. So the way that we interface with, different modalities, either visual data, robotic agents, or data itself. Traditionally, his work has been in the space of computer graphics and animation. He was the person that actually created and established our undergraduate computer graphics class, and we always find it fun to show, even decades ago, what our students were doing in this class. These are kind of like illustrations of like some of the projects that a student in his class kind of like have been delivering, and we always try to modernize it and make it kind of interesting. But historically, this is what he had been working on. But he has also moved to creating virtual worlds on the screen, to creating physical worlds kind of like in robotic environments. Now, the best way to actually see that in person is to actually come to the graphics lab across the street. We have an open house from 2 to 4, and there's going to be robotics demos over there. It's kind of like an interesting interplay where exactly there is a crossover between visualization and robotics. You could actually have situations where you have combinations of both. You could have either visualization of robots, you could have virtual environments that describe and author and control virtual robotic agents, or you could have VR interfaces for robots, or you could use visualization-oriented tools in order to train robots to do tasks. So it is kind of like a very cross-linked, kind of like a circle. So after having touched on those topics, and again, come to the demos, I'm going to talk a little bit more about the human data interaction aspect of his work. And typically that goes under the umbrella term visualization. But more in a more fine-grained way, it's split up into visualization, research, practice, and education. So what are the scientific kind of like theoretical contributions, how to help other people in other domains use visualization to their advantage, and education help others do it. So visualizations, the research, many of the components that go over there is perceptual studies, understanding how visual stimuli actually come across to observers and what is the message that is being conveyed, technique designs, systems for investigating visually data, and explorations of various principles that can be applied in the design of such systems. And there's a little bit of everything in what he does. So he's worked on text viewers that focus your attention on most pertinent parts of literary corpuses, and project that was called Text DNA also was able to kind of like slice into pieces of literary work and identify specific traits that would point your attention to some works rather than others. He has also worked on topic model comparisons, splatter plots, and different ways of combining visual modalities like point clouds and area plots in order to convey the most important information of data, and so on and so on. Some of the projects that are a little bit kind of like more visual and easy to kind of grasp on is visualization of protein structures. And this is something that, you know, you can use to highlight functional traits of molecules and how those interact, articulate, and exercise their function. And finally, I'm just going to talk a little bit about some of his more recent kind of like visualization projects. And this is a tool for exploring scientific literature, scientific specifically. You know, for example, like there's tons of papers out there. So how should we focus our attention? The AI component of this system has to do with recommendations, so finding papers that are similar and creating a visual to-do map of what is the space of kind of like similar papers, and then using several tools, have some search tools that can use some starting point in finding relevant additional works, map them out into 2D, and give recommendations of specific items from that collection. And the answers that are being offered for that is, why did you recommend that? Is it relevant? Is there a different way to look at this work? Are there groups of this work that kind of like come in clusters, and also understanding a little bit of like, why is this recommendation coming in like this? Why is this particular piece of work in this cluster? What does it mean to be there? And where else should I look in order to have a more holistic view? Okay. And once again, please stop by the lab for demos and other projects. We are going to be there from 2 to 4. And finally, a few things about myself. This is going to go really fast. So my interests are in physical-based modeling, digital humans, simulating the world, fluid animations, making things fast, making things break. So I have worked on digital humans, muscles, swimming humans, characters in animation, and how to easily animate them for artists, how to simulate hair for visual effects, how to use suturing and cutting for simulating visual surgery procedures, how to use virtual surgery simulations in a training environment and in clinical settings, and how to design and prototype surgical operations so that you can actually practice on a virtual setting instead of an actual patient. But sometimes you also use these techniques that are used for cutting people, for also just breaking things up. So some of our tools were used in production. So for example, like you want to smash up kind of like the hamster's ball in bolts, or create cracks, or destroy things, or create smoke and fluid effects at very high resolution. Use adaptive simulation for fluids and make them fast. Use simulation of complex media, such as fluids that are containing kind of like sustained particles. So, like sand and grain suspensions of fluids, or just general slicing and dicing. We like cutting things and colliding with things, and making interesting visualizations of them. Okay, this is a little bit historically of what I have been doing, a little bit more of what I have been recently interested in. Something that is a very big thrust right now is doing design of solid structures, with not just by using our expertise or kind of like our guesswork of like what works well, but actually using optimization tools in order to give us the best design. You might have seen 3D printed, everything from kind of like support structures, the tools, devices, bicycle parts, vehicle parts, and everything like that. And you can see that sometimes the 3D printed designs have unconventional shapes or structures. And this is because it has emerged from an optimization practice that this particular way of depositing material would be the lightest, strongest, kind of like most effective. This is one example of a design where we're saying, create a bridge, a suspension bridge that fits in this box and needs to occupy 5% of this box. It needs to have the maximum amount of support of anything that is on the base platform. And you see that we get all of these like very intricate filamentary structures that create kind of like support at the very end, and can actually minimize weight substantially. Other things about control that are interesting to me is in virtual humans, just using complex control in muscle-driven systems in order to do intricate tasks. In this particular case, we were doing juggling. And in general, something that I've been very interested in is using heterogeneous computing and pretty much everything that we can get our hands on at a very high density in order to increase the scale and complexity of simulation. And a very big part of my work these days is also working with motion picture studios. Two recent collaborators were Weta Digital and Disney Research, and some other more recent stuff with NVIDIA, but this is not in my presentation. In the interest of only being able to fit a few things in there, I just wanted to put two recent things in my presentation. This is a recent work that we did with Disney, and it has to do with an AI assisted system for aging and re-aging actors. So what you see on the left is the actual actor performance of, like somebody on the wild. And on the right, you're going to see that actor de-aged by 10 years and then re-aged up by 10 years and then by 20 years. So I'm just going to play it. So the input is on the left, and what is automatically produced is on the right. Okay, and this is plus 10 years. The interesting thing about this is that it's not a controlled environment, it's a natural environment. So, and this is like plus 20 years. But this is robust to kind of like lighting changes and kind of like interesting environments, and still kind of like was pretty plausible. I could have shown you more, but then I needed to get special license for that. So that would have been difficult. Talk to me privately. Some of the work that we did with Weta Digital has to do with creating models of actors' faces, but instead of the traditional way that we did it, like I did it in my research, which was to put down, some collection of muscles and bones and everything like that. In this particular case, we tried to do it completely based on data. So we have no idea where the muscles are or anything like that. What is the underlying mechanism? We just have lots and lots and lots of data for the actors. Can we figure out how we can create a simulation-oriented puppet that I can turn knobs and essentially just get the right behavior out of it? Okay, and that runs me out of time. Thank you so much. Happy to talk to you later.
Can I just use this to control the slides or? It's just- Oh yeah, perfect. All right. So good morning. My name is Pedro Morgado. So I'm gonna present the work that we've been doing here in computer vision. So just to start, is there a way to play this video? I don't think I can. So I just want to start off with a demo from one of the faculty here in the lab, but it may not be working. Yeah. But okay, so we can kind of move on from there. So yeah, so computer vision. So what do we mean by computer vision? So here, basically, it's like any type of task that involves images. And you can think of that as identifying what objects are in images or videos, where they are. Like you can do at the pixel level or just broad localization, like in object detection. You can also think of objects that are articulated. And so in that case, you might be thinking of the object parts that compose that object and trying to identify where are those parts and how those parts integrate with each other. Things like 3D prediction. So basically depth, trying to predict these depth fields from single images. And there are many other applications. This is just a few of the applications where these types of research can actually help quite a lot in the real world. So you have from, of course, autonomous driving. You need to identify where are the lane, where are the other cars, so you can make good decisions. Automated retail stores. One interesting application that starts to become like very useful is just digital painting, and you can try to control. It could be things as simple as you just write down a prompt and the generated AI will just give you an image that responds to that prompt, but you can even get more fine-grained than that and basically try to provide an image, a picture of just the semantic labels of what are the things that you want at different places, and then just feed that to your algorithm so that it can draw the fine-grained details. We also do a lot of work in computer vision. Can also be useful for things like medical imaging, agriculture, face filters, and stuff like that. And so, as you can see, like this can actually, it's a very highly interdisciplinary field, and we routinely use tools from optimization, statistics, physics, optics, electronics. We have to deal with how the images are acquired, not just how to interpret the images. And things like even things from psychology can be useful in computer vision. And so these are the folks that are doing the job here at in Madison. So you can see, there's 5 faculty, me on the top right, Pedro Morgado, and then you also have Young-Jae Lee and Mohit Gupta in primarily in CS, and Vikas and Yin Lee in the BMI department. BMI stands for biostatistics and medical informatics, but also collaborating quite closely with a lot of folks here in CS, and they also are associated with CS. Total, there's about 25 students doing all of the great work, and there's, of course, like a lot of regular meetings and collaborations happening across the different groups. What I want to do is basically just kind of go into each one of our works and what are our main research areas, as we basically kind of span all of the different types of applications and research areas that I was talking before. So starting with me, so I'm an assistant professor, primarily appointed in ECE. I do a lot of work in computer vision and deep learning, and the main thrust of my research is about trying to understand visual data without having to annotate a lot of the images, without having to collect a lot of the human supervision, because that can become quite complex and quite expensive to do. The other research trust is on trying to learn from and use associations between vision and other modalities that would be correlated with it. And with that, we can both learn better visual models or be able to achieve tasks that you wouldn't be able to do otherwise. So here's just a couple of the, a couple of the different projects that we've been working on. So in the self-supervised learning area, so I work both during doing a lot of the pre-training, how to learn large models without using human supervision. Here is a few examples of applications of the things that you can get out of that. And for example, like you would be able to discover new visual concepts in your data. Perhaps like you're trying to deal with the data sets that you still don't know what are all of the things that are in your data, and you still are in the discovery phase. So a lot of these techniques could be useful for that. In the case of multimodal data, you can also do things like speaker identification. With respect to multimodal perception, that's another big trust in my lab. And here, what we're basically trying to do is there are many applications that we try to deal with. One of them, one interesting application is how can we basically identify in the image or in the video where are the objects that are actually producing the sound, and beyond that, try to identify all of the objects that are producing the sound and try to separate the sounds that are coming from each one of those objects. We also work on, we start working on multimodal generation as well. And here, there are many potential applications for this. You can simply just think of having a video and try to generate the audio that it comes, that should come with it, or the opposite. One of my prior works is actually trying to find the locations of the different objects and try to generate this audio that it could be used in a VR environment. There should be another video there, which is not playing, but you could think of generating this audio that when played in a VR headset, you'd be able to listen to where are the different sounds are, where are those sounds are coming from, and they would be synchronized with the actual locations of those objects. Oh, this one actually played, but in the long run, wow, this formatting really went wrong. So in the long run, the idea, the big level idea in the things that I'm trying to do is really trying to think of how we can interact with the world through all of the different modalities. I think that vision, audio, text will still become the major modalities, but in order for robots and machines to actually interact with the real world and be able to make decisions in the real world, then they have to also be able to interact with other modalities like tactile and like how a robot would interact with the world. So now moving on to Youngjae, he's an associate professor in CS. His main research team is on understanding visual data with minimal supervision. So pretty much aligned with the things that I do as well. Here, he actually has done quite a lot of work before in topics like image recognition, object detection, and segmentation. Actually, one of the clip that didn't play at the beginning was a demo from his lab where he was basically showing how to do object detection basically in real time with very high performance. He's also been working on things like image generation, and more recently, not just learning to generate images, but also learning to identify which images have been generated by AI. So basically the problem of deepfake detection. And he has done work on other things like privacy preserving recognition and working with first-person video. So he actually maintains, has quite a big lab and has a lot of interests that happens all the time. And so here are just a couple of the ongoing projects that he keeps an interested in. from self-supervised learning, semi-supervised learning, video understanding, point clouds, object segmentation and detection, multimodal learning. So quite variety of different problems that he keeps working on. And a lot of this work, similar to me, is basically published in conferences, ML conferences and computer vision conferences, CVPR, ECCV, ICCV, NeurIPS, the usual ones. Mohit is another computer vision faculty here in Madison that works a lot in computational imaging side of things. So what he's interested in is in designing novel cameras and vision algorithms for applications in robotics, interfaces, and scientific imaging. One of the ongoing projects that he has going on is developing computer vision and machine learning techniques for emerging and exciting cameras called single photon cameras. And so these are cameras that are extremely sensitive down to individual photons. And so with these cameras, they can enable computer vision systems to perform well in conditions that are very adverse, even like extreme dark, or when there's quite a lot of light. And so these are now actually starting to become mainstream, and you can even find them in your iPhone, which uses a single photon camera for 3D imaging in the dark. And so his work has resulted in a lot of publications and patents, as well as a lot of industry collaborations. One of his broader goals is to develop these computer vision systems that can work reliably in very challenging real-world conditions, such as outdoors, in the dark, with strong sunlight, bad weather, underground. So anything that normal cameras would usually struggle at, these new types of cameras would potentially be more robust, and you could get more information out of them. And the goal is that these computer vision systems can be deployed in real world and have very practical impact in applications like self-driving cars, augmented reality, many different applications in robotics and automation. So now Yin Li, he's an assistant professor at BMI. He, beyond computer vision, he also works a lot in wearable computing and biomedical data analytics. And basically the research team that he has built is how to understand human activities and the implications in their health by analyzing videos and wearable sensor data. So these are just a couple of different applications in video analytics. Like, of course, you have to think of if you're trying to understand how the impact in their health, then trying to understand what people are doing and where people are in the video, that would be very helpful. So he actually publishes still quite a lot in core computer vision problems. And then on the wearable vision computing, he has developed a few sensors for example, tracking hands and stuff like that. So finally, the last professor that I need to talk about is Vikas. So he also does a lot of work in computer vision and in statistical imaging analysis for imaging and data analysis problems in biomedical sciences and for machine learning. Here's just a couple of the recent and ongoing projects. He works in fairness, as you can see, diffusion and differential equations, efficiency in transformers, uncertainty calibration for scientific applications, and non-decomposable losses in vision. And just one project that I would like to highlight to finish off is this one, where this is basically try to address fairness, which is a key socially relevant issue in AI and machine learning. And it turns out that due to the properties of the data and of the algorithms, a model is able to cheat by using attributes that are correlated with the label, but would be otherwise not relevant to the classification task at all. And so in this ongoing project, Vikas and his collaborators are working on algorithms that are applicable to these settings, as shown in one of the data sets that he has developed. Here you can see that these activation maps indicate that this algorithm, FAIR ALM, is able to conceal gender revealing attributes in the image. And so with that, you'd be able to predict complete the prediction task without using these correlated attributes that could impair fairness. And with that, so that was the last slide. I'm glad you guys are here and come talk to us, join us.
So just a few quick announcements. You have about a 15-minute break now. Try to be back. I was just thinking about how much the department has grown in terms of the research faculty we have and the collaboration between what used to be really sort of discrete areas. They're all coming back together. So there's a lot of information I know that's been thrown at you this morning. The talks will be recorded and posted on the Welcome Weekend website afterwards. So if you want to go back and look at any of that, you can. A few announcements about the schedule this afternoon. Faculty are going to join us for lunch, and we want to have some faculty at every table so
Okay, guys. Thank you. Let's start the next session. Hi, everyone. Do I need to use the mic? Oh, no. Now I cannot move around. Yes. I like to move around. Thank you. Thank you, guys. Thank you for coming. Welcome to Madison. My name is An Hai Duan. I'm from the database group. I have been here for too long, I guess. But I'm here to talk about to start the session and also to talk about the database group. Okay. Many of you probably know that, the database group is a very distinguished and very old group here at CS at UW-Madison. The group was started by David DeWitt back in 1976. That was when I was still in diaper, and maybe your parents are still also were in diapers, right? So the group actually have done a lot over the years. So what happened is that, they made giant contribution to relational data management. Pretty much everything that we do today in relational databases can be traced back to the group. If every single one of you is having a smartphone, you are having at least one relational database system on that. It's called SQLite. The technology on that has been traced back to here. And, we also have had our graduate everywhere, right? In various top ranking CS department, and also as a Microsoft fellow, IBM fellow, you name it. So the group has had a very long and distinguished history, and it's a kind of hard to live up to that. Okay. So today the group actually has 4 faculty members in the order of hiring. So I was hired probably like 17 years ago. And then actually this is not even in the order. So I was hired, and then Jignesh, then Paris, and Sang Jiao. I'm originally from Vietnam, but I have been here for 30 years. And then Paris is from Greece, Jignesh is from India, and Sang Jiao is from China originally. And we still have a lot of distinguished people around, and we have a pretty large groups with more than 30 students. So let me tell you a little bit about each one of us. So hang on. Okay, so this is me. The only reason that I'm first is because, I got hired first, really, like the oldest guy in the group. So what I do is I do basically data science. Okay, so if you think about data science, what you need to do is you need to take multiple data sets. Then you need to clean and integrate the data set together. Then you have one clean unified data set. Now you could run analysis on that. Okay. And I am working on that first part. I'm working on how do you take multiple data sets? How do you pull out structured information from that? How do you clean, explore, integrate, match those data sets? And then, people could come in and do the rest. And that first part is usually taking 80% of the times. Okay, so it's a very significant part. And these days, it is at the heart of everything. For example, when people talk about AI, they talk about data-centric AI, meaning you need to have a lot of data to make AI work. You cannot have a lot of data if the data is dirty and in different places. You need to clean and integrate them. As an example of a problem that I have been working on, take a look at these 2 tables. These 2 tables talk about people, right? Like a name and phone and address and things like that. A very simple problem is called entity matching. How do you figure out that a tuple in one table is the same as a tuple from the other table? They both talk about the same person, right? That's it. The problem is very simple to state. Well, how hard is it? Well, if you have a good solution, this is a $1 billion startup. You come talk to me. We will do a startup. We split the revenue, okay? In fact, a few years ago, I had a machine learning based solution, and it was really not that good. And yet I was able to do a startup with 2 PhD students. And then basically we sold the startup to a Silicon Valley company. And I actually disappeared the last 2 years working in Silicon Valley. And I just came back in September, right? So imagine what happened if you could have a better solution, okay? So that is the kind of problem that, I have been working on. Next, this is Jignesh Patel. He is at the other end of the data management spectrum. So I'm working on the semantic machine learning, that kind of thing. And he is working at the low level system hardware stuff. He's looking at how to improve relational databases on new hardware, how to do data analytics on new hardware. These are basically two major goals that are guiding his research, right? How do you build a single uniform analytic, platform, and how you make it run very fast on existing and also new hardware. So he's really like a system kind of guy, okay? But at the same time, he is also working on startup. So he's having a startup called DataChat. DataChat is sort of like a chat GPT, but presumably a lot more reliable. Otherwise he would kill me. So basically, you could go and you talk with DataChat and you could say, tell me, where can I find data for customers and something like that. And it will do that, right? So the startup is somewhere here. Then the next person is Paris. Paris is basically the theory guy. He is doing a lot of theoretical stuff. And he also work on algorithmic issue, right? So one of the major things that he's working on is parallel processing. Parallel processing is obviously critical because you have so much data, right? But a lot of parallel processing does not exploit the topology of the machines underneath. And his research is looking into how to do that. That is just one of the issues. He has also been working on machine learning and how to price data for training machine learning and stuff like that. Another thing he has been working on is, again, cleaning data, basically for training machine learning solution. So this is Paris. And then the last recent hire is Sang Yao. So we hired Sang Yao a few years ago, and he's working on cloud databases, right? It's very sexy, hot topic. He's looking at how to take relational databases, move to the cloud, and exploit cloud properties in order to make those databases work much, much better on the cloud, right? And he is also looking at hardware. As you know, GPU is absolutely critical for the AI revolution. You cannot have ChatGPT unless you have GPU. And he's looking at how to work with all this new hardware like a GPU and stuff like that, okay? So to summarize, the database group here has had a very long story, has done a lot of very cool stuff. We currently have plenty of people working on the entire spectrum of data management. If you want to do anything from theory, okay, to machine learning, to parallel processing, to very low level hardware, to cloud, we have it. And we have very strong connection with Silicon Valley. We work with them, and we usually have a problem that if we create a startup, they buy it. So it is a little bit of an issue because then we need to fly back and forth. And we are also looking to hire 1 or 2 more people, especially someone who is doing a lot of machine learning. So hopefully we will see you in the fall and hopefully in data management. Today, we actually have an open house between 2 to 3. I think it's listed. And if you guys want to talk with any one of us, just drop us an email, okay? Thank you. Is that? Thank you. Angela, am I on time? 4 more minutes. Let me try to do the whole thing again. Actually, I planned for that contingency. So is anyone having any question? And where's the next speaker, by the way? Oh, you are right here. So then why do I need to, yeah, okay. But still, anyone having any question? Feel free. Yeah, go ahead. Where's the open house? Yeah, it is in the OCS building, not the new one, which is still like a hole on the ground, okay? But in the OCS building on the 4th floor, just go up there, look kind of lost, and you will find us, okay? Yeah. Any other question? Yeah. That is wrong. Yeah. See, that is a data cleaning problem right there. Yeah. So yeah, it's a 2 to 3 today. The reason it's a 2 to 6 is because I took last year's slide and then I cleaned the data And my cleaning is clearly probabilistic because it didn't clean that. Yeah. Okay, guys, I wish you a lot of success when doing the PhD. I was sitting right where you sitting 25 years ago. I still remember that, you know. So, you know, best of luck wherever you go. And I hope to see you in Madison. Thank you.
Hi, I don't have a startup. I'm Loris Antoni from the MedPL group, which stands for Madison Programming Languages. And in our group, we try to answer this question, should programming be painful? So the answer is probably yes, but maybe not. Maybe we can make it better, I don't know. So this is a computer and there is coffee next to it. So that's a very important pairing. But people use computers to write programs, and apparently people write a lot of programs. So I'm sure you wrote some programs, probably. Otherwise, if you didn't write a program before, that's interesting. Yeah, you chose computer science. But it turns out that people write a lot of programs, and programming is also changing a lot. Like now people write different programs. For example, write programs that run on data centers and do complicated stuff. And the more complex programs, like Anhai said, you have to clean your data to send it to magic machine learning devices. And those magic machine learning devices learn stuff, and that stuff then is used to do bad stuff. For example, machine learning these days is used to decide whether you get a loan from a bank or whether you get admitted to grad school, maybe not here, but hopefully not anywhere else. But anyway, programs have permeated our society. They are everywhere. So hopefully we should write programs that don't have bugs, or that they do the thing we want them to do. Okay, sounds good. So that's what our group is about. We're gonna build tools and frameworks that help programmers write software that meets their intent. So when you try writing programs, you have something in mind. We want you to get that with everything you have in mind and turn it into a program. And that's what our tools are supposed to help with. So that's what programming languages research is at the high level. Is like, how do we make it easier for people to write programs that do the thing they want? And this is important. This is a pretty old article that says that apparently it costs money to fix bugs. So we don't want bugs. Actually, it's pretty funny. This is from 2016. And then I'm preparing another talk. And I was like, oh, let me check what the new data is. And the new data said it's 60 billion now, the cost. So maybe it got better. Or maybe just, I don't know, the data was wrong. The data is always wrong. So it's OK. So we have to account for that. But in general, bugs are costing not just billions to repair, they also cost a lot sometimes, even if you fix them very quickly. So for example, when networks go down, companies lose a lot of money. And so the programs that cause the networks to go down, they probably should be correct, or they should meet the the network configurator intent. And this is what I was hinting at before. Now people are using software in the form of machine learning models, or even in the form just of software, to make decisions in this world. And it's becoming a bit tricky to decide when the software meets the intent. So this is arguably, my opinion is that software shouldn't be used to decide whether somebody should go to jail. But some company apparently has done it. And then, of course, people have found out that the software had many false positives for one race instead of another, which meant that one race was more likely to go back to be resentenced unjustly than another. And this is really bad. Like, this is like, you know, if you have a bug in your quick start, life moves on. But if you have a bug that causes somebody to have a very, very bad outcome in their life, that's a really bad bug. And so we need to really understand how we can help people write software that does the thing they want. So what should we do? Well, what you should do is become a PL researcher so that you can solve this problem. And these are some people. So this is the PL group, is us, me, Somesh, and Tom. And then there are 2 illegal PL people. So they do PL, but they do other things, but they also do PL. So anyway, I didn't ask them to put them on this slide. So I think Ethan is here and Tej is probably also here. But we have 2 new faculty, Tej and Ethan, that they do systems and security, but they use a lot of PL stuff. And in general, everybody uses PL. They just don't know it. So this is our group. And we are apparently pretty good. according to the metric I chose, we rank pretty well in this country. So what is interesting here, I think we are a pretty, so there is this website that tells you a number, and the number is high is good according to this website. But basically, if you put programming languages and logic, which are the things PL people in this department work on, it turns out we're pretty good. What is interesting, noticing we're actually second now by some epsilon thing, but notice how many faculty contribute to this number. So we do a lot of work here, even though we have 1/3 of the faculty of the next one, we have more or less the same number. So this is just like means we're very prolific, but who cares? You know, getting papers is important. But I also am going to show you that we do actually interesting research, which is probably the more important part. And we work on a number of things, but in general, our group works on 3 things that are verification. So making sure that there is no unintended behavior in your software. Maybe repair. Can we fix the software automatically to not have the bug that you found? And maybe why do we need to look for bugs at all? Why don't we just automatically generate software that does the right thing? And all of these these are kind of like the main things we do. And I'm going to show you some examples of how we do it or what we do. So what is verification? So as I say, you give some intent, some specification to the program and the program verification engine is this magic thing that says, yes, your program meets the specification. So it's a good thing. Or it says no, in which case usually there is a bug, a counterexample, something that you can look at as a programmer and say, oh, this is so sad. Maybe you fix it. And so let me give you some examples of some of the work that has been done here. For example, Tom Reps, he has done his work on, you can give it a C program, and you can give it some complexity specification. You can say, does this program run in n log n? And he will figure out how to do that automatically. And there is a lot of interesting ideas here using concepts from discrete math and solving these recurrence equations. And he has built a lot of tools that can do this type of analysis for you. Why would you care about the complexity of a program? Well, there are settings in which complexity matters a lot. For example, this day, all the rage is about smart contracts, which apparently already are in their dark age. But so when smart contracts were cool and Bitcoin was worth something, people cared a lot that your program wouldn't waste resources because the resources were money. And so that's one of the reasons you might want to work on this. Okay, so it turns out machine learning is not yet at the next dark age, so it's still working pretty well. So one thing I've been working on a lot is trying to verify programs in the form of machine learning models. So machine learning models are just programs. They're just programs that have that are easy to generate automatically. But at the end of the day, as I say, these programs can be used for weird stuff. For example, they can be used to decide whether you get a loan. And you might want to ask as a verification question, had there been some noise in your training data, would you have learned a model that assigns loans in a similar way? And so this is what we call data bias. So this is essentially, we have settings in which we know there is historical bias. So essentially the data you train the model on, it's probably slightly off for whatever reason, maybe because there was noise, maybe because it's been crowdsourced, or maybe because the world has been a terrible place for the last 40 years and people have done things that they were not exactly fair. And so we have some data that says, oh, you know, these people have unfairly been denied loans, so maybe we should account for that. And so what we are building is basically techniques where we can reason about, oh, what if there had been some bias in the data? Would you have learned a similar model? And so an example of a question you might want to verify is if an attacker, which in this case can be malicious, accidental, or whatever, had changed 1% of the data in any way, would you still have learned the same model that does the same, a similar model that does a similar prediction? And why is this programming languages? Because we work with logic and programming languages techniques on top of these models as if they were programs. And we treat the training algorithms themselves as programs. So it's a program analysis question. So if you thought programming languages was just programming languages, think again. It's also machine learning. Okay, so what is synthesis? Synthesis, so yeah, finding bugs is cool, but program synthesis says, why don't you just tell me what you want, and I will come up automatically for you with the program that meets the specification and the proof that the program does the thing you want. And it can also maybe say such a program doesn't exist. So if you ask for giving you a program for something that cannot be done, maybe you need a proof that that cannot be done. And going back to the bias example from before, we've done work where essentially maybe instead of checking whether a model is robust to bias, maybe we can have techniques to automatically generate a model that is provably robust to the bias. So this is again a combination of machine learning and programming languages techniques to generate models that have provable properties. So usually when you use machine learning, data in, model out, and who knows what happens. But here we have ways to basically generate models that come with proofs as in mathematical proofs and logical proofs that the model does the thing you want. Okay. So another project that I'm working on with Tom is this idea of building synthesis frameworks. So synthesis has been used for a lot of applications. So for example, in my group, we've used it for automatically fixing programming assignments for students learning programming so that we can give them feedback when they're learning. We've used it to generate automatic data extraction techniques, like you give examples of the data you want to extract, we generate regular expressions or something for you. And we've also used it with us in repairing programs that make decisions like loans and whatnot. So now the question is, okay, every time we have to come up with the technique, we have to come up with the technique, we have to come up with the technique. Eventually we get tired, we say, why don't we just design one framework, one programming language of synthesis, where you can essentially solve all the synthesis problems in one place. And so this is one of the projects I'm very excited about, where essentially it's a programmable framework where you provide a synthesis problem as an input and you get a synthesizer for free. So basically, the hope is that any synthesis problem you will have to solve where you want to generate programs automatically, this framework will be able to accommodate it. So if you want to know more about, you can come find me, or probably some of you are already talking to me about this. And there is also a PL open house, which is not on this slide, but you got the email probably with the detail. Finally, Ours is working on this new project of a quantum compilation framework, where the idea is that people write quantum programs, apparently, even though there are not many quantum computers out there. And the thing is that these quantum computers, these devices where these programs are going to run, they keep changing and new ones keep coming up. And it's very hard to basically compile your program to these architectures efficiently because they keep changing and they're all a little different. And so Ours is working basically on synthesizing the compiler itself automatically. So essentially, when a new architecture comes in, you come up with a new compiler that is efficient at generating programs that run on that architecture. And again, here kind of the ingredients are always the same in programming languages. We use a lot of logic, we use a lot of formal methods, techniques, and all this fun stuff. So to conclude, this is what the PL group works on. And basically, software is everywhere now, and we should make it easier for people to write. And these are kind of the three macro areas that you can find here. Questions? Yes. Yes, yeah.
Out of curiosity, how are you verifying intent behind a neural network model? Those are like notoriously black box problems.
Okay, so, well, there are two questions. So how are you verifying intent, and are the notorious black box? So, well, we have techniques that are white box, meaning that they actually perform some kind of analysis on the network itself. So they propagate some information on the network so that we can get proofs out of that the network does something interesting. But we also have techniques that work at the black box level. And so essentially you can do things like, oh, maybe you can train multiple networks, and then if they all agree on the outcome, you can get a very strong argument that the attacker has failed or something. I can tell you more in person, but there are ways to essentially do both black box and white box analysis. Other questions? Okay, there are no more questions. I'm looking forward to see some of you today, and go to the PL Open House, which I don't remember exactly what it is. I think it's 2 to 4 in some room, but you'll find the information. Okay, thank you.
Hey everyone, my name is Matt Sinclair and I'm going to present on the computer architecture group here. So although we didn't plan Laura's presenting directly in front of me, it is very well ordered and timed because he told you about how we're going to make things easier to program. And now I'm going to tell you how we're going to make those programs run fast. So that's largely what we do in the computer architecture group. In case you don't know, before I move on, actually, in case you don't know, there's a number of us, Swamit, who you're going to hear from next, right after me, talking more about the quantum computing you just heard a little bit about, as well as Miko Lapasti, Karu Sankaralingam, Josh San Miguel, and Guri Sohi, as well as some others who dabble a little bit in computer architecture. So for those of you who aren't aware, the computer architecture group here has done a lot of fundamental and foundational research across the years in many different spaces of the field. And we can think about this as a timeline, starting roughly in the 1970s, way before my time and most of your times, when the 4004 came out. And at this point, we had single core uniprocessors. And Moore's Law was alive and well, giving us 34% annual growth with, minimal extra effort. At that point, all this hard stuff Loris is telling you about to make programs run faster, we could just let the hardware, kind of handle that for us at that point. So we didn't need a lot of extra dollars or a lot of extra power to do it. And a lot of this work revolved around foundational work that now emeritus faculty like Jim Smith, Jim Goodman, Mark Hill, David Wood, did during that time frame, along with Guri Sohi. And as we move through the years, as uniprocessors started to fade out and multi-core and accelerators became more and more common, as Moore's Law started to fade, we see this ongoing transition that, again, a lot of us, including myself, have played a role in innovating and providing foundational work in. And ultimately, there is a big question, which Swamit's going to tell you a little bit more about in a couple minutes here, about what comes next as those kind of solutions fade out, quantum computing certainly being one of them. But ultimately, that future, similar to what Laura's told you and what Swamit's going to tell you next, is going to include AI. It's going to include ways to have tighter co-design with software. And a lot of this is being driven by the fact that Moore's Law, depending on who you ask, is either dead, dying, or slowing, depending on your point of view. I know the Intel CEO just had a talk at Hot Chips saying it's alive and well, at least through, I think he said 17 angstroms, which is an impossibly small size to think about. But nonetheless, regardless of whether you think it's dead, dying, or slowing, there's a lot of really interesting questions that we as a group are working on ways to try and solve. And of course, like I said, AI is going to play a big part in that. AI with ChatGPT and Microsoft's recent equivalent solution that already got taken down and offline have shown a lot of promise and require a lot of optimizations at the hardware level when we talk about ways to make them run better. And of course, quantum computing is coming qubit by qubit and will eventually play a role, and it has lots of really interesting questions about how that will integrate with more traditional kinds of computing, whether they be CPUs or accelerators. So why might you want to come and do computer architecture research here? Well, we have a very strong history, as I alluded to. We've done foundational work in a number of these different spaces, which you can, of course, read on the slide, but they go from uniprocessor techniques to multi-core techniques to simulation infrastructure. If you've ever used tools like Gem5, FarmSim, GPU-Sim elsewhere in your work, students and people like myself have played a big role in building, designing, and maintaining those tools and adding support to them. And at least personally, I find that really, really cool because it allows you to see things from the bottom all the way up to the top and ensure that the kind of things that we're publishing in our conferences have basis in reality and are representative of the kind of things we're trying to run. And likewise, our present is very strong. We're doing lots of really cool work on coherence, consistency, optimizing GPUs or heterogeneous systems more broadly, looking at security or transactional memory or virtual addresses and so on and so forth. And all of us in some way, shape, or form have won very prestigious awards in the community, whether that like Guri Sohi has the Eckert-Mockley Award, which is the highest award you can get in computer architecture, or being ACM IEEE fellows like Guri and Professor Lapasti are. or all the way down to dissertation awards or NSF career awards. Or Karu recently just returned from a very successful chip startup where he built a line of chips under the name Mozart that did some really, really cool things with general purpose AI. And so we have somewhere around 20 to 30 graduate students with several well-funded projects working on this array of stuff. And it's not just the current students that are doing well. We also have students who have graduated and gone on to do really, really good things. You're going to hear Yelena talk about a couple of those examples tonight at dinner. But just to give you a few examples, we have a lot of former students who've gone on to other places, around the globe, Europe, Asia, and the US at other big universities who've won major awards and done very high impact work there. And likewise, we've had other students who've gone on to industry who've done really impactful work across basically any major processing company you can think of. Most recently, down the street in Google-Madison's office, the TPU processor was done here largely by former graduates of our program, at least in the version 1 program. And the AMD Zen line of processors, one of the AMD fellows who's leading those projects is a former alum of Miko Lepasti's group. So we have, people both in industry and academia who've been in your shoes, who are sitting in a room just like this one, who've gone on to do really great things. And I apologize for the formatting issue that things are off the bottom of the slide, but the hope is that you will come and be that next great person who's doing really high impact computer architecture research and driving the community forward. And in 5-10 years, we can add your name to this list, and you can be the one who we get to brag about to that next generation of potential students. So just to talk a little bit about what we're doing, and just like Loris, I know we have lots of one-on-one meetings set up with all of you for this afternoon where we can talk about them in more detail, or people like Swamit and myself will be around at lunch and dinner if you want to talk to us more about them then. Swamit's group, I'm going to keep short because he's going to tell you more about it in a moment, but largely he is working on quantum computers. You heard Loris tell you a bit about some of this work that he's doing with Aus a moment ago, but he's also doing some work on cryogenic architectures that I think is really, really cool. And if I may, do a humble brag for Swamit for a moment, he had a paper published 2 years ago that's already been cited over 300 times by other people in the community. So an evidence of really, really high impact work that he's already done. Karu's group, I mentioned he not only does research here, but he had a successful startup, Simple Machines, where they built the Mozart chip line. And what he does in his group is vertically integrated architectures. So going all the way down from the transistors up to software. And so really what he's been looking at right now is how do we design what he calls general purpose accelerators. So if you look at your smartphone, for example, like a modern Apple phone has somewhere between 50 and 80 different accelerators in it, which is a lot. And it's only going up and up and up if you look at the trends from the last 10 years of Samsung, Apple, et cetera, smartphones. And realistically, we don't have enough area in a very small form factor to keep increasing that over and over and over. So we're going to hit some wall, some limit there where we can't just keep throwing in more and more accelerators into the system. And so what Karu's group is looking at is, well, is there a way we can consolidate that down and have some smaller number of accelerators that are still able to provide very, very high performance for more than one, say, different kind of workload, where those different accelerators in your smartphone are each optimized to perform some very specific task. And in the past, you might be aware that he's won a number of awards for doing stream data flow acceleration, including some of his former students now having gone on and done great work on that as well. Professor Sohi's group is focused on uniprocessor and multi-core design. Although some of the community have moved on from it, it's still really, really important. As Gary likes to say, this is useful for the 99.9% of people who use CPUs in their programs, which it turns out is still all of us. And so in the past, this has resulted in, like I said, foundational groundbreaking research in speculative multi-threading, out-of-order processing, load store queues, amongst other things. And in recent years, he's been looking at non-traditional multi-core architectures, looking at ways along the lines of what Laura said to make it easier to program those kinds of systems, as well as security. In Miko's group, he is looking at a number of things, including system and processor design. And if you're familiar with Miko's work, you might know that he's also famous in the past 10 years or so for having worked on non-traditional architectures. So looking at ways to design spiking neural networks or to model the human brain, not in the way that the current deep neural networks, machine learning kind of thing has, but truly modeling the human brain at a hardware level. So really cool stuff. In addition to that, he also has been working on novel, power-efficient cache coherence and interconnect work, including photonics, for those of you who are interested in that kind of space. And some of his current students are also looking at what do we do when we have what he calls bitstream computing. When you only have like 1 or 2 bits wide of a processor, how can you efficiently do computation, say, with edge computing type devices? And in addition to that, he's also done, again, some really, really foundational important work that's won Test of Time awards in the community with high ILP processors with low power and low complexity. In my group, what we focus on largely is looking at how to optimize data movement in those heterogeneous systems. So general purpose GPUs are the most common example of this, but my group is also looking at ways to extend this to other kinds of accelerators. And in the past few years, that's largely focused on questions like how do we design memory consistency models or cache coherence protocols, or how do we organize and move data in those systems? But moving forward, what my group is focused on is thinking as we move into a new design paradigm where we're moving from monolithic processors to chiplet-based processors, where instead of one big piece of silicon, you have many small pieces of silicon that you're connecting together in an effort to help with some of those, if you will, concerning trends about the end of Moore's law. This is where the community is going. And there's some really interesting questions about when we break up our monolithic chip into a bunch of separate chips, how do we design the control plane? How do we reason about the best or even a good way of organizing and moving and scheduling data between these kinds of things? And that includes optimizing the tools. As I mentioned, Wisconsin Architecture Group is famous for building, maintaining, designing a lot of those tools the entire community worldwide uses. And I'm the maintainer, one of the maintainers for the Gem 5 project. So my group does a lot of work in that space as well. And finally, Josh's group is focused on energy efficient or energy centric computing. In particular, Josh has done a lot of really, really cool work on the edge, looking at when we have sensors or other kinds of very power constrained devices, how do we make them run things in a reasonable amount of time, since oftentimes with their batteries, they can only run for so long. And this has included looking at things like approximate computing, all the way down from the circuit level up to some programming language work, which won the Best Paper Award at ISCA last year, which, if you know, is one of the top computer architecture conferences, or maybe the top computer architecture conference. And this also includes energy harvesting. So in that case, using solar power maybe to charge these chips and the implications of designing chips that way. So to end, I just want to leave you with 2 things. So if you're interested in doing this kind of work, we have a website that details everything I just said here and more, which you're welcome to visit. Like I said, people like Swamit and myself will be around all day, and we're happy to meet with those of you who are interested in doing this kind of high impact work to make all that cool stuff you're hearing about from all the other groups run fast and efficiently. We need efficient hardware, and that's what the 6 of us are doing. And we also have an open house with our students that's going to be 3:30 to 4 in the set, which is in Union South, directly across the street. And we'll have some soft drinks and stuff there, so you can chat with our students in a more informal manner. So I'll corral a couple students to help guide people there if needed, but simplest way is just directly across the street from where we are right now. So I'll end there. Are there any questions I can answer? If not, then I will let Swamit tell you a bit more about the quantum computing specific part of what I just referenced. Thanks, everybody.
Okay, thanks, Matt. That was really amazing presentation on what we are doing as an architecture group. So I'm wearing a different hat when I'm talking about quantum computing. We are a really young group. We don't go back to 1980s. This is the first time I'm going to talk about quantum computing. And I'm super excited because, when we think about computing, it's always a full stack problem. And I'm going to convince you that quantum computing is also a full stack problem, right? So before we get into what are the stacks and how to build a quantum computer, let's try to answer some simple questions. Why do we want to build a quantum computer? Because classical hardware or conventional hardware is pretty good. You can build a supercomputer that can churn a lot of numbers very quickly. You can train really big models using these supercomputers or data centers. So why do we want to build these new type of computers which are using these quantum properties? And simple reason is there are problems that conventional computers cannot solve. Even if you build a really gigantic, say, computer that consumes all the energy of Earth, that spans maybe, half of the Europe, you will still not able to solve some of the really hard problems like factoring numbers, right? And the reason we use these problems in our encryption systems is because they're very hard to solve using conventional computers, right? You will take probably hundreds of years or even thousands of years to factor a 1024-bit number. But what's interesting about quantum computers is quantum computer can solve that problem in few hours if we can build one, right? And it's not just factoring. There are many problems in machine learning. There are problems in chemistry, which we want to solve because we want to build better drugs. We want to build better batteries. We want to build better materials, right? And those problems are very hard to solve using conventional computers. And the promise that quantum computing makes is some of those problems can be solved by building these new type of machines, right? But it's not going to solve. It's not going to solve all type of problems, right? There are certain problems in chemistry that you can solve very quickly, and the reason we can solve these problems quickly is because if you think of how we encode information on conventional computers, it's just a switch, right? You have a bunch of bits that you kind of orchestrate to do computing. On a quantum computer, we have this quantum bit. I don't know if it's going to show up. There is an animation, but you can think of it as you have a state of this device that's much, much richer than the binary state of conventional bit or classical bit, right? And when you perform operation, you not only switch between North Pole and South Pole, you can actually rotate on the sphere. It's called like block sphere. So suddenly, instead of having just information of 1 or 0, you have information that's kind of analog in nature, and you can process that information very efficiently if you build a quantum computer, right? But as I said, quantum computer is not going to solve all type of problems. In my opinion, it's going to be an accelerator, something like GPU. GPUs are amazing because now you get this insane amount of parallelism that you use to train machine learning models. So it solved significant problems in machine learning, but you don't use GPUs to solve, let's say, GPUs are not running operating systems and they're not, doing word processing at this stage, right? So similar to GPUs, quantum processors or quantum processing units will be accelerators, but it will be a different type of accelerator, right? So for quantum computers, you need to sort of think about two things. One is these quantum devices themselves, which hold this information that has some magical properties that you want to use to solve problems. And the other part is this control electronics that controls these devices, right? And it's kind of interesting to think about both of these components. And we are doing that here in Wisconsin. We have a very influential physics department. They are building these quantum bits. And here in CS, ECE, and other departments, we are thinking about how to build control electronics, right? So the interesting thing about quantum accelerator is they reduce the complexity of solving problem. Unlike conventional accelerators, where you get the speed up by running n parallel threads, but you get this like a constant factor speed up. Whereas on a quantum computer, there are certain problems where you can reduce the complexity, and that gives you exponential or polynomial speed up, right? So that's why we want to build quantum computers. They solve really important and hard problems. And you may think that this is all kind of fiction. I don't know. Nowadays, there's a lot of media coverage on quantum computers. So maybe you already know about this one interesting news that back in 2018, Google built this 53 qubit machine. They have these 53 qubits. They put this chip in a refrigerator, and they can run experiments or they can run programs on this quantum chip, right? And what they did was they created this problem that they could solve in 200 seconds if you run it on a quantum computer. But if you want to solve the same problem using a supercomputer, it would have taken like 10,000 years. I apologize for formatting there. It's 10,000 years, right? So you can see a significant speed up that you can get by building these quantum computers. And that's something that many companies are thinking about. So this is a roadmap from IBM. They have delivered on this roadmap so far. So today you can actually run program on a 433 qubit machine if you have $1 million, because it's like super expensive to get access. But again, if you have @whisk.edu email, you can run programs on 16 qubit machine. We have some connections with IBM, right? But people are thinking of building bigger and better quantum computers, and they want to solve harder and harder problems, right? One of the challenges in making quantum computing more sort of appealing, or frankly, we have not solved a real problem yet. So one of the challenges in doing that is this problem of noise. This information that gives us the superpower of solving problems fast is very fickle. It vanishes. It just decays very quickly, right? And that's like a fundamental problem. So you can prepare these states which have magical properties, but they decay very quickly. They decay within a microsecond, right? The other problem is when you're performing operations, there is a large probability that the operation that you're performing is incorrect, because this is like, think of it, right? So when you're rotating on the sphere, if you rotate a little bit more or a little bit less, that's an error. In a digital computer, that's not a problem. We have quantization. Here we are dealing with analog information, which is extremely sensitive, right? So how do we sort of mitigate these errors is one of the problems that physicists, computer scientists, and engineers are focusing on, right? So one of the things that we can do, wow, this went really bad, is we can run error correcting algorithms, right? So just like in a classical or conventional computing, when you get an error, you have this code that tells you, hey, there is an error. We can do similar tricks on a quantum computer. One of the problems on a quantum computer, though, is this running error correction is extremely expensive. So what we try to do is we perform collective operations on these physical qubits, right? Whenever you want to perform an operation, don't just perform it on 1 qubit or 1 bit, you perform it on hundreds of qubits. So you get this redundancy, right? But it's costly, right? And I just showed you that we have 400 qubits on the latest and greatest IBM machine. So we have a long way to go, and that's something that industry understands. So this is another roadmap from Google. Recently, they did this demonstration where they created this one fault tolerant logical qubit, which can tolerate some of the errors, right? And they have an intention to build this error corrected quantum computer that will probably look like, I don't know, like a really large machine with millions of qubits, right? But there are a lot of challenges in going from 100 qubits to million qubits. And that's something that we are trying to sort of, think about here at UW-Madison. So I talked about, computing being a full stack problem. So if you think about whenever you're using a computer to solve a problem, you need to perform this series of transformations, right? Let's say you want to solve a problem. First thing that you do is you figure out what type of algorithm you want to use. You code it up using your favorite programming language, compile it down to the hardware that you have. let's say you have x86 machine, you pick an architecture, and somebody has to build that architecture. Somebody has to optimize that architecture. So all these problems are there when we are building quantum computers also. And just sticking Q in front of algorithms and just sticking Q in front of architecture, it's not that easy. There are like significantly different constraints. For example, on a quantum computer, you cannot copy information. It's a really bizarre model. If you're writing a program, you're not allowed to copy variables. You're not allowed to create temporary variables. And now we have to sort of also worry about noise, right? So there are so many challenges that we need to solve before we can exploit or leverage the properties of qubits. So we, in CS department, we focus on algorithms, programming languages, compilers, and architecture, right? So on a quantum computer, you have lot of moving parts, right? You can think of quantum computer as you have a bunch of lasers that you're attaching to FPGA, and this lasers are focusing on these qubit devices. And when you want to run a program, you're writing a program in Python, right? Then you convert it down to this some type of assembly code, and you do series of transformations, and eventually your program is just sequence of these laser pulses. Now, when you are sort of writing this program, when you're debugging this program, you need a lot of support, you need a lot of tools, and that's something that we think about, right? So there are a lot of computer science problems when we are building quantum computers. There are also a lot of engineering problems. One of the problem is we need to keep these qubits at extremely low temperature. So this is kind of a nice figure. This is like a dilution refrigerator. We probably have 6 dilution refrigerators on campus. They're in physics building. If you open this, you can see this chandelier-like structure. The chandelier-like structure is actually a refrigerator. At the bottom of this refrigerator, you keep qubits. You run wires to control these qubits. The wires go to FPGA or some type of computer, right? So we want to build this setup and run problems that we cannot solve using supercomputers, and that's going to be very challenging. One of the simplest challenges, if you keep your FPGA, which is controlling these qubits at room temperature, there is going to be limit on how many wires you can run, because wires are good conductors of electricity, also good conductor of heat, so wires will leak. So eventually we want to build a processor which sits at this 4 Kelvin temperature, extremely low temperature, and that can control these qubits. And so we also want to sort of think about how do we want to architect this overall system, because at 4 Kelvin, you cannot dissipate more than 1 watt of power, right? And if you create a lot of noise, if you generate noise, that's going to leak to your qubits, and all the computation will be destroyed, right? So this may seem like a science fiction, but it's something that people are already building. They have created some really solid systems, and we need to sort of think about system level, architectural level, and algorithm level solutions to solve some of these problems. So in the near term, we are thinking about how can we mitigate these errors by using software and hardware techniques. We want to scale these systems so that we can go to this scale of thousands of qubits, and eventually we want to sort of think about new application, new algorithms, new abstractions, if you will, so that we can get this exponential speed up, not just on factorization or drug discovery problems, but beyond that, right? And that's something that we are sort of excited by. So we as a group focus on quantum algorithms. Also, once quantum computers become sort of available, encryption systems that we use today are no longer very effective. So we also want to think about what should we do when there are these quantum computers. So Rishabh Goyal, who is a new faculty here in CS department, he thinks about what kind of cryptographic protocols we should use once we have quantum computers. So it's post-quantum cryptography. Aus and I, we focus on programming languages, compilers, and architecture for quantum computers, right? So there are 4 of us. We kind of think about from theory to architecture, And we have a lot of interesting courses. Dieter teaches this advanced quantum algorithms class that he's teaching this semester, and that's kind of gives you a foundational overview of what are quantum algorithms. I teach a class on quantum systems and quantum architecture. We talk about how to build compilers, how to build architectures that can scale so that we can build a 1,000,000-qubit machine, right? And we are lucky to have really amazing students. We recently started a couple of new projects where we focus on compilers, building simulators that are very fast. We are also thinking about how to build a 1,000,000-qubit machine, which is distributed. We also think about post-quantum crypto as a group. And recently, we got a lot of success in publishing these works at top venue in PL conferences and architecture conferences. So with this, I'll conclude my talk. If you have any questions, shoot me an email. I'll be around for lunch and dinner. Unfortunately, we don't have open house, but shoot me an email and I can figure out something. Thanks for listening. Oh, if you want to talk to some of my students, they will be there for the architectural open house. So just find my students and during like architectural open house.
Hey, good morning. Welcome to Wisconsin. So my name is Josiah Hanna. I'm an assistant professor in the department, and I'm part of the robotics group, which is what I'm going to be talking to you about now. I'm also part of the machine learning group, and Kirthi will be saying a bit more about the work there. So these are the professors in the robotics group. We have Professor Bilge Mutlu, Professor Mike Gleischer, myself, Josiah Hanna, and then Mohit Gupta, who is also part of the computer vision group, but working on robotics work. So today I'm going to talk about the research of the first three of us, Bilge, Mike, and myself. Please, come talk to us later if you're interested in the work. There's also going to be a couple of different robotics open houses. So Bilge and Mike students work on some things more related to human-computer interaction, human-robot interaction. So there will be one open house for them, and then some of my students will be available in my lab to talk as well if you're interested. Okay, so first, this is going to be talking about the People and Robotics Lab. So this is work. This lab is led by Professor Bilge Mutlu, and his work focuses on the interactions between people and robotics. I'm going to mention just first of all that while I'm going to talk about these as like kind of three separate labs here, there's a lot of collaborative work in the department. So it's not like you're siloed into a lab if you're working with a robotics professor. But very likely, you might be working with a couple of different robotics professors or even people not in the department. There's a lot of collaborations with robotics folks in engineering. So let's see if these videos will play. Those will not. So. Okay, then I'm going to talk about these without some videos here. So one of the kind of key research questions that the human people and robots lab is looking at is how do people interface with robots? How can people control robots and get them to perform useful tasks? So for instance, robots provide a lot of benefits to people in, say, industrial environments, that robots are strong, they don't get tired, there's no wear on their bodies the same way that there might be for a person who's doing some hard manual task. So one goal is that maybe we can have a person actually, do a task themselves, but in some way where they're actually controlling a robot to do the task in a way to make their manual labor much easier. So to do this effectively, you need to develop good interfaces for the robots. Because it's not necessarily, if you have a robot arm that has like, it's not quite the same morphology as a person's arm, then it may be like very challenging for the person to control them to get them to do a task correct. So part of this research involves trying to develop good interfaces which allow people to intuitively control robots. Another important aspect of this research is asking questions about what happens when we put robots out in the world and they are cohabitating human environments with us for a very long amount of time. So in this one project that Bill Gates' lab has done, we've looked at social and educational robots and trying to, in this case, design learning companions. So robots which you might have a child who's trying to learn to read or learn some other skill. And the robot doesn't do a whole lot in terms of, actually like affecting the environment directly, but it provides an emotional companion, providing guidance to the person, encouragement, trying to get them to, keep working at the skill. And so, you could do like a small scale study of this. You could, maybe bring a person into your lab, but that's not quite the same thing as what's going to happen when these robots are freely available for everyone to buy, and they end up spending very long deployments with people. So this research project is, interested in doing field studies in educational settings, just studying like, how do people like over time interact with these robots? There's of course interesting privacy questions which arise in this setting as well. Another work kind of related to interfaces for human robot interaction is developing programming tools. As we start putting robots out in the world, we're going to need to script behavior for robots that hasn't been foreseen by the people manufacturing the robots in the first place. So in this case, you want to develop tools which make it easy for users who maybe have lower technical skills to kind of quickly develop good behaviors for robots. So in collaboration, we have an excellent programming languages group here. And so there's been some collaboration between Bill Gates' lab as well as ALS on developing tools to kind of automatically generate behaviors and also verify that these behaviors accomplish the intended goals of the user. Okay. All right, so that's the human and robot interaction lab. So now I'm going to turn over to Mike Gleischer's research. So Mike's work is concerned with visualization, graphics, and human-robot interaction. So in the way that Mike likes to put it is that there you have human and graphics interaction, where you're how do people generate images, videos, animations. Human-robot interaction, how can we make robots easier for people to interact with? And then human data interaction. How do we visualize data? How do we make data easy for people to understand? So when we talk about visualization of robots, we might have a robot that's engaged in some behavior. We want to make it easy for people to understand what the robot is trying to do. And this could be useful for controlling the robot or just knowing like how you should respond to what the robot's doing. So for instance, this is showing one example of a visualization tool here to show how the robot is choosing different key points to move through in a particular motion, as well as there's some visualization tools where a user is using a VR headset to see the world through the robot's eyes. Here's some other examples of problems that Mike's interested in working on. So how can people specify the right actions for a robot to take? A lot of times as people, we bring a lot of knowledge about how tasks should be done in the world. And so, in this case, we can just train robots by showing them what to do instead of having to explicitly program them. We might want people to directly control robots. For instance, having, if I move my arm like this, I want to see that the robot arm also moves like that so that you could get the robot to do useful tasks. People being able to interpret the motions of robots, as well as people being able to monitor robots effectively. And if, for instance, a robot is doing a task and gets stuck and can't figure out the right thing to do, alerting the person to be able to monitor, to step in and help them. Okay. So this is also an instance of kind of this controlling of robots. In this case, what you have is that you have a robot arm that has a very different morphology of the human arm, but the person wants to control the end effector of the robot's arm in an intuitive way. So we want to see that like as the person moves their arm this way, that kind of the end effector part where the gripper is on the robot should also be like moving in the same way, even though the precise way that the joints up the arm moves is going to be quite different between them. So in this project, this is called bimanual control, where you're somehow aligning what the person does with the robot in order to control it more effectively. Related to visualizing what robots are doing to help control them better. This was another project from Mike's group where we have one robot which is performing a task and another robot whose job it is to provide informative viewpoints for a person controlling the robot. So to help kind of understand the situation a bit better, imagine that like, these robots are deployed on another planet or they're deployed in a dangerous environment where we can't put a person like right there to see the world through their own eyes, but rather we have to rely on some sensors that the robot has. So if you're a person, maybe you're like a NASA engineer back on Earth and you're trying to control the robot, the viewpoint that you're receiving of that robot is going to make a big difference for how well you can effectively accomplish your task. So this work is looking at, how we can have a different robot arm, which has a camera mounted on it to try to give the most informative viewpoint. Answering research questions like this is not just a matter of working on robots, but also doing user studies. Like the end goal is people and making things, easier for people to do. So here's a case of a user study where this is kind of simulating this case of where the people are in a different location than the robot. So there's a divider here. People are using the laptop interfaces, but the robots are behind the divider accomplishing the task. So the person can't rely on their own perception to control the robot, but they have to rely on what the other robot is showing it through the camera. And all of this work that I've talked about so far is collaboration. While I'm talking about it in the context of Mike's lab, it's a collaboration with Professor Bilge Mutlu as well. In some more recent work from Mike's lab, we've been looking at sensing for robots. And this is one challenging problem of trying to put sensors on a robot to be able to like perceive its environment. And how do you handle miscalibration of the sensors or when the robots, you don't know exactly where the sensors are? So this is a kind of a more advanced type of sensor that's been developed by Professor Mohit Gupta's group. But you can kind of conceptually think of it as like a laser rangefinder. So for the sensor, you can just imagine it's sending out like a beam of light, which tells you how far some object is. And so if you have this type of sensor on your robot, it can like help it place itself in its environment. Like the laser rangefinder hits objects and it tells you, okay, I'm that far from that object. And you can use just simple geometric calculations to figure out what the right distances are. But a problem in practice is that even if you have very tiny error in where that sensor is on the robot's body, so let's say in this case, the sensor is mounted to a robot's arm and you think it's in one position, but actually when it was installed, it was kind of just slightly off. These small errors can end up giving you very large errors in how you perceive your environment. And so what they've been looking at is how can you automatically calibrate, even if your sensors are in the wrong position, how you can detect where they are, as well as calibrate what their distances mean in terms of the environment situated in. And so there's a lot of interesting applications that this can be used for instance, just robots localizing in an environment or mapping an unknown environment to begin with. So this is work that was recently published, but where this is kind of currently going with a current project is being able to inspect unknown areas. For instance, maybe you want to like sweep the surface of a truck bed to see if there was like an illicit substance in there, or you want to go into a dangerous area and detect if like there could have been radioactive material on the floor or something like that. So this gives a problem called sweeping, and in a completely unknown environment, the robot has to be able to like place itself in that environment very well, and then also know like, has it actually covered the whole area in this environment that it's never been in before. So some planned research, going to be trying to do this with this quadrupedal Boston Dynamics spot robot, where you have an arm on it, which can kind of provide the sweeping of the surface, but the robot is not just it's not fixed to a table, but rather it's got to move around to cover the entire space. So some of the interesting research problems are just, how to, convey the objective to the robot. How do we program good motions for the robot? How do we know what the robot's plan is going to be? And that it's good. How can the robot be monitored if it's performing this task in some dangerous environment? And how do we, at the kind of end of the robot's performance, confirm that it's done a good job if we can't actually be in the environment with the robot? So I'm going to next talk about, switch over to my own research. So I do less work with humans and robots. In fact, I focus more on autonomous robots, and particularly how robots can learn to achieve their goals through interaction with the world. So the real world has enormous complexity and variation. We kind of see this in like the autonomous driving industry, where there's just like so many cases. There's a very long tail of challenging driving scenarios that the autonomous vehicle industry has not been able to accomplish, despite billions of dollars of investment. And what this means is that because there's so much complexity in the real world, it's impossible to program the right actions for a robot or an autonomous vehicle to take in like every possible situation it could encounter. And so to develop general purpose intelligent agents, we really need agents that can learn. And that's what the area of machine learning called reinforcement learning focuses on, is developing robots that can learn from rewards and punishments through their own experience how to accomplish tasks. So reinforcement learning has been used in many different application domains. One of the core challenges, though, with really extending it to robots in many situations is that while it's been used very impressively in games and simulated environments or very data-rich environments, it tends to be very data inefficient. So, for instance, to learn to play a video game, an RL algorithm takes 50 million actions before it learns to play it, whereas probably any of you can learn to play a video game in about 5 to 10 minutes of interaction. This board game of Go took millions and millions of games, the computer playing against itself, to learn to play well. And one more example from robotics of the robots taking 1.5 years of compute to learn some skills. So one area of my research looks at using simulated robots as a kind of surrogate. We can learn directly in simulation and then apply what we learn onto physical robots. I think I'm almost out of time, so I'm going to skip a bit through my videos. So what's happening here is this is a project in which we have a robot that can walk in simulation, and we also have a robot that can walk in the real world. And so what we want to do is we want to apply reinforcement learning in the simulation, where we can just throw compute at the problem and not worry about the time it takes to collect data on the real robot, and then have that transfer onto the physical robot. So in some of this research, right, so in some of this research, we applied this to a now robot walking, and we're able to speed this walk up. And so it was the fastest walk that we knew of on this robot. And we just, instead of like hand tuning the walk as people had done previously, all of the learning happened with reinforcement learning. One current project, which is ongoing in my lab, is we're trying to, in many cases, it's hard to construct a high fidelity simulation of a task environment. And so, those aren't showing either. We're trying to move towards learning in much more low fidelity simulations, where we don't try to model the world perfectly, but we try to model it at enough of detail that learning can still progress and be deployed on the real robots. So if you're interested in seeing some of the, since I don't have the videos, if you want to see some of the output of this, you can stop by my lab, CS 1351 later, and you can ask my students for a demonstration. The last thing I have to say is that just my research is not just robotics. It'll be briefly talked about in the machine learning presentation, but I also look at fundamental and theoretical questions in reinforcement learning, as well as applications in non-robotics domains. And the last thing I want to conclude with is that there's, the 4 of us in computer science working on robotics, but we have a much larger robotics ecosystem at UW-Madison. So these are, you can go to this robotics.wisc.edu/people and see some of the other exciting work which is happening in the engineering department as well as computer science. So with that, thank you. I look forward to talking with many of you all later. And if you're interested in any of this work, please check out the robotics open houses. Thank you.
All right. Okay. Good morning, everyone.
I'm Kirti. I'm a machine learning faculty here at UW-Madison. I'm also new faculty, so I'm new to the city. So if there's any questions you have about, what life is like at Madison and how do you adapt to it, you can come and talk to me. I will be at lunch, so if you have any questions, you can always come and speak to me. So I just want to give an overview about the machine learning group at UW-Madison. And, this is like a rough categorization of how we think about machine learning here, like the faculty. We have the robotics faculty you heard from Hosea just a short while ago. There is the vision faculty, there is biomedical informatics, and there's, of course, people who work on machine learning. So this is like broadly we categorize AI into these 4 groups. But it's not that. There is faculty like Yudong is speaking about the optimization research here and so on. So it's just a rough way for us to kind of group the faculty. And there is a lot of faculty here working on AI. So I think the top row are the faculty whose home department is computer science. But there are also faculty, actually Hosea is also in CS, but there are also faculty who are in ECE, there's faculty in statistics, and there's also faculty in biomedical informatics, and there are also faculty in the business school. I gave a talk at the business school last week, and there are people who are interested in doing machine learning and in fact do machine learning. But I just wanted to for most of this talk, I just focus on the faculty who work on the CS faculty who work on machine learning. And you may have heard about or will be hearing about some of this faculty already. So Yelena and Steve, I think Yudong will talk about them when he talks about optimization. Hosea just spoke right now, and Elias, I think he's probably covered in the TCS talk already. So I just focus on some of the other faculty and give some of our research highlights, right? Right, so Yudong, I'll skip this because Yudong is going to talk next. But I think broadly speaking, I'll quickly go over this. He talks about, he works in the intersection of machine learning and optimization and how you can use optimization in machine learning, such as how do you optimize a neural network, and then also how to use machine learning to optimize systems. And here you can use ideas from reinforcement learning, bandits, and if you're optimizing black box systems, you have to learn about the system while you're also optimizing it. Hosea, let me skip this and then let me talk about some of my work. So I work on a spectrum of related topics. So in the intersection of bandits, online learning, game theory, and economics. So this is mostly motivated by the fact that if you think about AI systems today, they are deployed in the real world, and they affect the decisions taken by these AI systems affect many stakeholders. But at the same time, the algorithms need to rely on these stakeholders for some type of feedback, for some type of data. So there is a lot of strategic interplay between these algorithms and the stakeholders. So just a couple of use cases that we are thinking about. So one of them is on e-commerce platforms or something like Amazon or eBay. These systems are generating a lot of data. There are purchase decisions. Did the customer purchase or not? Sometimes if they purchase, they make a review. And then there's information that's being generated on the seller side. And the question is, how do you use this information to design a more efficient market so that the right customers buy the right things, and you create a situation where customers are happy and also the sellers are happy. But also, how do you kind of make decisions so as to collect information? So for instance, suppose you purchase an item, you're likely to get a review, but you get that review only if you make that purchase. So if for whatever reason the price was set too high and you did not make that purchase, now you're not gonna be able to submit a review. So sometimes it's useful to keep the prices low, not just because even though it leads to poor revenue, sometimes it's good to keep prices low because that way you can collect information about purchases and collect information from customers. Another application that we are thinking about is on data sharing platforms. So nowadays, people kind of recognize that data is very valuable. So there's a lot of people realize that data is like a very, very valuable resource these days, and that's thanks to the popularity of machine learning. But because of that reason, there's also people are very protective of their data. So for instance, if you're in a competitive market like a pharmaceutical or in a bank, you really want to protect your IP, you really want to protect your data, right? But at the same time, competitors might acknowledge that there could be a win-win situation. For instance, you might have some data that I need, I might have some data that you need, and we could exchange our data and we could both be better off because of that interchange. For instance, banks collaborate a lot on fraud detection. And so you could say, if it's a win-win situation, why don't we just go ahead and share this data? The problem is, as a competitor, because of you as a competitor, I don't exactly trust you, right? So I'm kind of worried that when you're giving me your data, you're going to corrupt your data, or you're not going to share your data honestly with me. So it is a machine learning problem, but there are a lot of game theoretic considerations that kind of come into play, because I want to make sure that by making these exchanges that I don't lose, and that no one else is trying to rip me off by giving me fake data in exchange for true data. So I chose to highlight these two application domains because this is more about using machine learning to design more efficient markets. And this is about designing a market, a data sharing market for a problem in machine learning. But there are other application domains that we're interested in. So for instance, one application that I've worked on is how do you share resources among multiple agents who are competing for that resource, when these agents themselves do not know what their resource requirements are. So this is about my work. And now let's move on to Sharon. So Sharon does a lot of interesting work on out of distribution detection and how you might do machine learning in the open world. And one of the applications she likes to talk about is, if you, for instance, take one of these classical convolutional neural networks, and suppose you deploy this convolutional neural network to detect objects when you're self-driving. It does really well in environments that it knows well about. So you're driving in the street, it knows to detect cars, it knows to detect buildings, it knows to detect traffic signs, and so on. But suppose you took this car, which you've trained on an urban environment, and put it in an environment like this. All of a sudden, these algorithms, they tend to perform very poorly. And you've seen, if you kind of see something like this, you see a rock and it detects that it's a car, for instance. And this happens a lot, and these machine learning algorithms can tend to be very brittle in situations that it has not seen. And that obviously is going to affect the decision you make. So for instance, if it's a car, you might expect that this car is going to drive and just go and stay behind it, hoping that it would drive. But if you knew that it was a rock, you might do something else. You might either drive around it, or if you see something like this, you might decide to turn around and drive back, right? So these decisions can have very serious downstream consequences. And how do you make these machine learning systems to be robust? So if you've only collected data over here, then at the very least, you should be able to look at this rock and say, I don't know what it is. But unfortunately, machine learning algorithms today do not do that. So that's Sharon. Let me next talk about Yingyu. So Yingyu works on a lot of theoretical topics on deep learning. So machine learning, people use a lot of deep neural networks nowadays, but if you look at the gap between theory and practice, it's quite large. And Yingyu works on trying to close that gap. When do machine learning models work? Do we always need to find the optimum over here? And is it sufficient to find a locally optimal solution? And is the neural network still going to do well? And some of his work has led to cool insights that has led to very practical use cases. So some of the things he's been able to show is that by designing nice optimization methods, you can make these machine learning methods robust to sensitivities like this. Right. Next, let me talk about Fred. Here, so Fred works on the limits of machine learning. So how far can you push the machine learning models, and thinks about how you can study guarantees when systems work and systems don't work. And the way he kind of goes about this is by studying, looking at machine learning methods from a more geometrical perspective and being able to reason about how these machine learning methods work geometrically, right? And he also applies these methods for how you might construct data. So people talk about supervised learning or unsupervised learning, but can you leverage some geometric structure to design semi-supervised or weak supervised learning methods so that machine learning methods can work with some weak supervision signals and be able to learn more efficient classifiers than if you're just using supervised learning alone. And then he also has a lot of cool work on data-driven systems. So this is some work in the intersection between machine learning and systems. So as machine learning people, we just think about using machine learning, think about the algorithm and then deploy it. But Fred also thinks about, how do you actually deploy this in the real world and how do you like design systems around it? And sometimes we tend to just look at it as a purely engineering problem. We just need to construct the pipeline to collect the data, train the model, and then issue all the predictions. But it turns out that there are a lot of cool theoretical insights you can actually think about when you actually look at the look at these data-driven systems. Then let me talk about Jerry. So Jerry does a lot of work in the adversarial sequential decision making. So sequential decision making is on bandits and reinforcement learning. Some of you might know what it is, but these have been traditionally studied in a stochastic sense. So the assumption is there is an environment, there's an agent interacting with the environment and observing reward. But if these rewards can be attacked by some adversary, how do you design reinforcement learning algorithms that are robust to these type of attacks? And he also thinks a little bit about the inverse problem of machine learning. So this is a question of how do you design training data to achieve a certain target that you might be able to state conceptually, but there is no way for you to kind of formalize it. And how do you kind of design training data for problems like this? And he applies this to a bunch of interesting problems, but one of the problems that he likes to highlight is on machine teaching. So here what you want to do is you kind of model a teacher as an attacker or as an attacker and say, okay, can you design this attacker or this teacher to be able to give you examples so that a student, or in which case is going to be some machine learning or reinforcement algorithm, is going to be able to learn in as few examples or as efficiently as possible. Right, so this is some of our core faculty that I kind of spoke of. But as I said, machine learning at UW-Madison is quite large. We also have collaborators in a lot of other fields. So here are some of the faculty who work on in the ECE department. So one of them is Rob Novak. So Rob Novak works in an area called active learning. So active learning is basically how do you design algorithms to be able to not just learn from existing data, but also collect the data so that it can learn efficiently. So supervised learning you think of as, okay, we have a bunch of data, we have a bunch of labels. How do you learn to map from go from X to Y? But really, when you think about intelligent algorithms, you think about algorithms that can go ahead and collect it to its own data. When you're learning something, you're not just learning what's being given to you. You also go out and say, okay, what else do I need to learn so that I can improve on things that I'm weak at, right? And that's exactly the principle behind active learning. So Rob does a lot of really cool work on being able to design algorithms that can, learn efficiently, but learn efficiently in an active sense. So you're collecting, you've identified that you need to learn about something, you go collect the label for that. Then you use that label, and now you can leverage that information to decide where else do you need to go and collect this data from. So Dimitris is another ECE professor. He works in the intersection between machine learning systems, optimization, and machine learning theory. And he applies them to problems in distributed training. So you have machine learning models. Instead of training them on one GPU on one machine, how do you train them on 100 different GPUs on 100 different machines? I'm a bit low on time, so let me quickly speed through some of these other collaborators. So we have Ramya. She's also an ECE professor. She works on more the theoretical side of machine learning, but with applications on crowdsourcing. So this is how do you learn from data that comes from people? And she has one of the applications she works on is how do you collect data when it's coming from people who are domain experts. So how do you have a learning algorithm that's trying to solve a certain task, but is also using a human expert in the loop to do this more efficiently? Then we have Kanwook, who is who works on, once again, some theoretical topics and information theory topics in machine learning. And he has applied some of his methods to analyze modern deep learning methods like GPT-3 and transformers. And he also has a lot of cool work on algorithmic fairness and trustworthy machine learning. Something I do want to point out, because Kanwook is the only one who mentioned this in his slide, is you can see that he has a bunch of EC students and a bunch of CS students he's advising. So it's just a way of saying that the machine learning community here is very collaborative. You are CS students, but you can be advised by ECG or statistics professors. And similarly, as CS professors, we also with students from other departments as well. So it's very collaborative here at Madison. We also have some collaborators on biomedical informatics. Let me quickly flash through the slides because I'm out of time. Yeah, and finally, I wanted to just mention a little bit about the community here. So we have a weekly seminar called Silo. So this is where we invite a speaker from outside and we ask them to give a talk. But in addition to this, we have something called a machine learning lunch. So in this case, it's mostly an internal community where the faculty and the students, both from CS, but also from outside of CS, who meet and discuss about research and their topics. And we also have something called an IFBA seminar where students who get to present their work, even if it's not exactly polished up, we encourage students to go and present their work. So there are 3 meetings every week in terms of a community that we have. Yeah, finally, I wanted to mention, nowadays it's very cold in Madison, but, Madison is really beautiful during the summer and the fall. So, keep that in mind when you're making your decisions. And finally, thanks for listening to this talk. And if you have any questions, you can ask me during lunch or during your one-on-ones if you've already scheduled it.
Right. Hello, everyone. Good morning. I'm Yudong Chen. I'm one of the associate professors here. I'm relatively new. I joined the department about 1.5 years ago, which is one of the best decisions in my life. So I'm happy to talk about it. So my research lies in the intersection of machine learning and optimization, but today I'm going to speak on behalf of the optimization group and try to give you an overview. So what is optimization? So optimization is very broad. Whenever you want to maximize something good, you can write it as an optimization problem. And by something good, I mean things like maximizing profits, maximizing reward, maximizing any kind of payoff. Usually you have some kind of constraint in terms of budget or time or resource. So you want to find the optimal solution subject to that constraint. And equivalently, you can also write any problem that involves minimizing a bad stuff as an optimization problem, like minimizing cost. So when you write things in this way, many problems can be cast as optimization problems. For example, any decision-making problem is an optimization problem, like planning a trip, making decisions in terms of your investment, choosing a grad school. For example, when choosing a grad school, you want to maximize, for example, the probability of achieving your career goal, subject to the constraint of budget or geographic location considerations and other personal constraints, etc. Moreover, many natural processes involve optimization. Many physical laws, like those that governs the movement of planets, can be stated in the form of an optimization. So optimization is incredibly universal and useful. But of course, you can write many things as an optimization problem, but it doesn't mean it's easy to solve that problem. So a lot of research has been devoted to developing efficient algorithms for solving hard optimization problems. And of course, many of these algorithms are inspired by the natural process or physical process. And these days, the connection between optimization and data analysis are becoming more and more close. In some sense, machine learning and data analysis is optimization, in the sense that when we work with data, we try to explain the data. And the guiding principle is to find an explanation that is as simple as possible. There can be many ways to explain a given data set, but usually the simplest one is the best one. So we want to maximize the simplicity of the explanation. So this is everything that machine learning and statistics is trying to do. And it can be phrased as optimization problem. And more specifically, optimization formulations and optimization algorithms are playing a fundamental and more fundamental role in data analysis and machine learning these days. For example, modern machine learning, for example, like training a neural network, heavily rely on first-order methods like gradient descent, or accelerated versions of it, or stochastic versions of it. Many machine learning problems involve matrix, optimizing over matrices. Many hard optimization problems can be solved using methods, the so-called alternating direction methods or coordinate descent methods, which scale very well to large problems. In fact, the connection between optimization and machine learning is so strong and so important that my colleague, Professor Steve Wright, decided to write a book on this topic, which is called Optimization for Data Analysis. And I believe this will soon be a classical book, textbook that is going to be used in many places. So to be a little bit more concrete, one of the most important problems in machine learning is supervised learning. So in supervised learning, I'm given a data set that has two parts. I have this data vector that represents the features of certain objects, and also I have the labels. And then our goal is when you give me a new data vector, I want to predict the label. So you can think of these data vectors as images. I want to predict whether or not they are dogs. You may view it as the recording of a speech in a digital form. You want to understand what's the words that are spoken in this speech. So many problems in machine learning can supervised learning problem. And supervised learning problems are optimization problems. You want to find a good model for prediction that has the optimal accuracy, prediction accuracy. And these days, data sets are getting larger and larger, so you need fast optimization algorithms. So supervised learning problem, there are two types of supervised learning problems. Classification problems where your label is a binary label that represents whether or not your feature vector belongs to one class or the other. You have regression problems where your label is a continuous variable. And many, but not all of these problems can be formulated as what's called a convex optimization problem. So these are relatively easy problems. There are many efficient and sophisticated algorithms developed for convex optimization. There is a very rich theory for convex optimization. But there are also other problems that arise in machine learning and statistics that are non-convex. So the prime example is training a deep nonlinear neural network, which involves solving a highly non-convex, highly nonlinear optimization problem. So there are active research going on into developing better algorithms and understanding when or why the algorithm works. So one of the most basic algorithms in optimization is gradient descent. Many of you have heard of it. So I would like to think of gradient descent as trying to slide down a foggy hill. You cannot see very far because it's foggy. So what you do is you just look around you, look at the neighborhood around you, and find the direction that is give you the steepest slope. So that's the direction mathematically given by the gradient, negative gradient direction. So you go to that direction, and then at a new location, you repeat. You look around your neighborhood, you find a new direction. So you will slide down the hill like this. And many algorithms used in training neural networks is based on this very simple idea. And so optimization lies in the intersection of many different disciplines. You already heard some of this in the previous presentation. So there are many initiatives on campus that try to bring people from different disciplines, different areas who are interested in optimization. For example, this IFDS, Institute for Data Science, is a high-profile institute that is funded by the National Science Foundation and led by my colleague Steve Wright in the optimization group. So it brings together faculties and students from math and computer science and statistics and beyond to work on problems that are related to data science and optimization. So IFDS supports many graduate students and postdocs. If you join UW-Madison and work with optimization faculty, you might get supported by IFDS, and you will certainly be participating in many of the activities in IFDS. So IFDS also involve collaboration with other universities, including the other UW and UC Santa Cruz and University of Chicago. And also we have another initiative called the Data Science Hub, which is led by Professor Michael Ferris, who is another member of the optimization group. And just let me talk a little bit about the research by Michael Ferris. So the research in the optimization group has impacts that goes well beyond academia. For example, Professor Ferris works on this problem of trying to distributing COVID vaccines to the people who need it. And if you remember, at the beginning of the pandemic, there is a limited supply of vaccines. So it's very important problem to efficiently and fairly distribute these vaccines. So, and this is a hard problem, and it's an extremely important problem. And Professor Ferris has applied some of his work in optimization, including multi-agent optimization and stochastic optimization to this problem. And his solution, his tools has actually been adopted by the Department of Health Service and the National Guard, who is doing really useful things using optimization. So let me just briefly overview the optimization faculty here. So we have 8 members in the optimization group. So 4 of them is in CS, so we call them the core members. But we also have affiliate faculties from industrial and system engineering and the electrical engineering. But of course, there are other faculties who are not officially in the optimization group but has interest in optimization. And we like to hang out on the 4th floor of this building, which is just across the street from computer science. So just a brief overview of each of them. So Professor Ferris, who I just mentioned, works a lot on applied problems that involve optimization. He's interested in problems that involve multiple agents, that involve distributed, decentralized algorithms. He works on applied problems in the space of energy systems, environmental systems, etc. Professor Steve Wright, who's another senior faculty in the optimization group, has very broad interest in all of continuous nonlinear optimization. And he is one of the leaders in trying to bring together people in machine learning community and from the optimization community. And he has written 2 of the most widely used textbooks on optimization. Professor Yelena Diakonopoulos, she is a junior faculty in the optimization group. He's interested in the intersection of the optimization and data science. And in particular, she's interested in problems that involve games, which several players are competing with each other. So you want to compute the equilibria, which is a generalization of optimal solution. She's interested in proving lower bounds, meaning that she wants to understand what can be done, what optimization can be solved, and what optimization problem cannot be solved, regardless of what algorithm you use. She is also particularly interested in connecting optimization with dynamical systems and control theory. So I myself is half-half between machine learning and optimization. I am interested in non-convex optimization problems that arise in machine learning and statistics. I'm interested in problems that involve matrices. And more recently, I'm interested in the optimization algorithms and formulations that arise in reinforcement learning. We also have our colleagues from the industrial and system engineering, and they are interested in discrete optimization, like integer programming, or mixed linear integer programming, and also in stochastic optimization. So this includes Jeff Linderoth and Jim Lukit, who both are experts in integer programming. We also have Alberto Del Pier, who is also in industrial and system engineering and works on integer optimization and polynomial optimization. And then we also have Rod Nowak, who you just saw from the machine learning presentation. So he has broad interest across signal processing, information theory, machine learning, and of course, optimization. So if you join us, you have the opportunity to work with any one of them. And finally, the optimization group offer many courses, from intro courses to more advanced one on nonlinear and convex optimization. And we also teach courses that lies in the intersection of optimization, data science, and statistics. All right, so I'm running out of time. I just mentioned that the optimization group has an open house. So you can come to the open house and hang out with our grad students. Thank you.
All right, everyone. So I am between you and lunch. So I'm going to keep it brief and then let you eat, okay? I'm going to present the HCI group. HCI, if you've never heard of this term before, stands for human-computer interaction, okay? All those computers that we're building, programming, teaching, learning, they eventually interact with people. And we in our HCI group work on how should people interact with these computers and what are the effects of it on people? Is it actually harming them? Is it helping them? And how do we actually design them so that it addresses people's needs in an effective way, okay? So I want to quickly go through the faculty we have and everyone's research. And at the end, I'm going to stick around during lunch. So if you want to chat about it, anything further, I'll be happy to do that. So we have 3 faculty members in this area, Professor Zhao, Professor Kim, and myself. Starting with Professor Zhao, she works on accessibility. She looks at different populations and uses technologies like augmented or virtual reality and generally intelligent technologies to assist these people, okay? So I'm going to give you a few examples of the kinds of work that she's done. So I've collaborated with her to see how people with low vision or people who are blind interact with their environment. How do they actually cook? How do they actually eat? How do they find their way in their homes? Do these displays that we all take for granted, do they actually serve them? Right? When something is on, there's a little light that says that it's on, and if someone doesn't see that, how do they know that it's on? Are they going to burn themselves, cut themselves? We look at things like that. And then we look at how do we build technology to assist them overcome those challenges, okay? This is a study of people using their kitchen environments and looking at the things that challenges that they have. They often have to use augmentative technology. They're not computer technology, but technology anyway. That looks like that. There are little glasses that give them a little bit of a sense of what's going on in front of them. Now, how can we do better using computer technology? Here's a project that she's worked on with someone who does vision research at the medical school, looking at how do people with low vision, and generally people with visual impairments are not all blind. A lot of them have just low vision, and they can maybe see what's kind of in their periphery, not in the middle. Maybe they have sort of distorted vision. They have a lot of challenges. So they look at how do they read. When you're looking at text, what are the patterns that you follow? What you see on the right here is the reading patterns of someone with low vision. And what you can do is once you model those kinds of patterns, you can adapt to them. You can introduce different kind of interventions like magnification. You can create contrast and just to help them read things more effectively. Professor Zhao has also been working on virtual reality. How do we make virtual reality more accessible for people who have certain challenges? If you're blind and if you're in virtual reality, which almost 100% relies on vision, being able to see the virtual world, see the other characters, see the things that are in front of you. How do you actually interact with these worlds if you can't see them? So they've created this thing called VR bubble. And if you're in certain proximity of different kinds of characters, they kind of announce themselves in ways that are not annoying, that increases the accessibility of these environments. Here's another example where if you're interacting with virtual objects, how do we actually make it more accessible to you if you have low vision? Can we explore these known techniques for increasing visual accessibility, like magnification, or can I use things like edge enhancement? Can I highlight the edges of things so you don't run into them? Can I do things like, well, I don't have a technical solution. Can I send it to the crowd and ask people questions about what it is that that's in front of me, and let people help me in a short amount of time? How do you actually create a pipeline for crowdsourcing these kinds of solutions? So exploring lots of different solutions. This is very interesting work. And then finally, if someone has a particular disability in a VR environment, they want to represent themselves, how do you enable to do them? If someone is deaf, for example, this is a user who's deaf, how do you let them express themselves in their avatars so that other people know that they're deaf and they're not trying to talk to them in inappropriate ways? And this is a solution where you see that the characters' hands are highlighted, so it's clear that they're going to use sign language so that people pay attention to that. So that's Professor Zhao. Moving on to Professor Kim, who works at the intersection of human-computer interaction and information visualization, which is another area that we interact with, because people interact with information, not just computers, right? They consume information. How do we actually make that more accessible and more effective? Professor Kim works on how to make data representations more accessible to people with impairments. So you open the paper, you look at some kind of data, maybe reading a scientific article. We're often interacting with a lot of data. We see charts, tables, pie charts, graphs, and things like that tell us something about data, right? If you have a visual impairment, that's sort of out of the question. You don't know what you're looking at. So Professor Kim, mainly in collaboration with Professor Zhao, are trying to solve this problem. So they look at things like, can I use text? Can I look at a chart and summarize it for people? And want to understand what are the kinds of questions people have for them, and using generated text to explain data to them. Or maybe we can use audio. Can I take conventional inputs like data types, quantitative data, ordinal data, nominal data, and then different kinds of conventional representations like bar charts and pie charts, and explore the space of how do we express that data, explain it to people in audio fashion, audio modality. And then finally, how do we make data tables more accessible? Because here we can't just summarize things, right? People want to know what's in that cell, in that column, in that row, right? How do you actually convey that? How do you help people navigate those tables? It's very interesting research, and it's very kind of impactful for people who have these kinds of challenges. And lastly, so I work in the space of human-robot interaction, and I believe that the robotics group also had a few slides for me. But I also apply those technologies, contextualize them in accessibility problems, assistive technology, and finally, I'm interested also in end-user programming. So I want to run through a few projects. In human-robot interaction, we build robotic systems. These are either companion robots, they might be social robots, educational robots, and we deploy them in real environments for long periods of time. So we have a project that we'd like to start soon where we're going to build a robot and put it in people's homes and families, with families for 9 months. And can the robot survive there? And if it does survive there, how does it build relationships with people? By the end of the 9 months, are people trying to kick the robot? Do they actually love the robot? Are they going to return the robot to us, right? Questions like that we look at. And then we explore novel robot designs. For example, let's go back. Can I have a robot express himself in novel ways? Maybe smoke coming out of his head. And what does that mean, right? The robot's frustrated. How do I actually express things like that? In end-user programming, we face the problem of we're going to be seeing robotic products very soon, right? Amazon is coming out with a robot called Astro, selling it now. And you can buy this robot, it can do things for you. How do you do that? Can you just talk? Is it sufficient? Can I just ask the robot to do X, Y, Z? Well, it turns out it's sort of underspecified. We start to try to solve those problems. So we give speech-based commands along with information on how to navigate the space and turn that into programs with single input, right? How to actually generate a program that the robot can execute using multimodal input about a complex task, but don't ask the user a million times what the robot should be doing, right? We also try to create motion that is natural for the robot, and how do we let people do that? And finally, if I have a collaboration with the robot, it's not maybe I'm trying to send off the robot, hey, go vacuum my room, but actually something I have to do with the robot. How do I create a collaborative program? Which turns out to be a very complex problem that touches AI, formal methods, user interfaces, very interesting stuff. And then finally, putting these technologies into these assistive and accessibility kinds of settings, we've been looking at how robotic systems can provide both physical assistance and informational assistance for older adults. This is a picture of a study that we recently finished where someone with dementia and tremor is being assisted by this little stick robot that comes along and then delivers water, ice cup, whatever the person needs. And we're looking at what does the person want? What do they expect? Are they scared of the robot? Should the robot run to them, or should it just slowly come? Should it announce first, or should it arrive, show up, and say, "I'm here"? Right? We don't know these questions. So we're trying to explore those things and letting people kind of tell us. This kind of work is done with a lot of community partners. So this study is done with a local community called Attic Angel. They are an assisted living facility. We also have projects with individuals with Down syndrome and people who've experienced brain injury who have very specific needs. For that, for example, working with an organization called Gigi's Playhouse in Madison. And these partnerships are very interesting. You actually go interact with the people that you're going to build technology for, you build them, you take it back to them and see what they think, right? This is sort of real test. It's not just some simulation where I show, that things are working, but we see it in the real world. So that's all I wanted to cover today. But to learn more, you can come to Open Lab events this afternoon. There are two of them. Professor Zhao's lab is holding one at 2 to 3 p.m. On the first floor of the computer science building. And then my lab is holding one at 2 to 4 p.m. on the third floor of the computer science building. And this is also in the schedule, okay? Thank you, enjoy your time here. I'm looking forward to chatting with you. And lastly, before I end, Molly has some announcements.
Okay, well, I hope you all enjoyed those talks. It was a lot of information for this morning, but it is lunchtime, which I know you're all anxious for. So a couple things. I created this QR code if you want to scan that to get the schedule for today. We've had a few updates to that, so make sure you get the most recent one. Remember that Angela sent you an email during this morning with the schedule of all of the open houses. So if you want to see in one spot where all of those are, make sure you check your email for that message from Angela. Lunch goes until 1:30. We're going to be opening up the wall here shortly, like we did with the breakfast and break. And if you had a dietary need like gluten-free, vegan, there's one person with vegetarian and gluten-free, there's a separate table with those meals. So if you did not say you wanted one of those, please don't take one of those because we're at the capacity there. Also, more faculty will be joining us for lunch. So please try to make room for them at your tables. They would love to meet and mingle with you. And as I'm sure you would like to meet and mingle with them too. And lastly, we'll hopefully see you this afternoon. It's kind of open time. You all have different things going on, but we'll hopefully see you back over at the Fluno Center, which is a few blocks that direction, for happy hour starting at 5:30 and or dinner starting at 6:30. So hope you have a good rest of your afternoon. And again, welcome. Thanks for being here. For those of you who joined online, thanks for joining us online for the live stream, and have a good rest of your day. Thanks, everyone.
Oh, really? Okay. Okay, so I just feel that the lot of work in general. And this can be yeah. How do we say okay? So are you? I guess, I mean, yeah, I was like, so, I had a really quick, I was wondering if like any future work in the space, like any other researcher papers that you, for us to review? Yeah, I think it might be, actually, so. We are. Well, kind of agnostic. Yeah, I'm curious in what you're thinking of this on this type of things. Yeah, so work on things like so right. Found one can combine. So that's probably what we'll do.